Welcome back to Sleep Nova. Sit back, relax, and enjoy the show. Before time, before space, there was nothing. Not darkness, not a void in which something could drift, for even darkness and emptiness require a place to exist. It was a nothingness beyond comprehension, a silence so absolute that no thought or word could pierce it. In that great silence before creation, no light shone, no sound echoed. All the energies and forces we now know were dormant or absent, in a state that defies human language. It is the canvas of non-existence upon which our cosmos would one day be painted. What does it mean to be born from nothing? This question has haunted philosophers and scientists alike. In ancient myths, the world emerges from chaos, from a giant cosmic egg or the spoken word of a deity in the void. These are human attempts to grapple with the ultimate mystery, how something, the universe, reality, everything we know, could spring into being when there was no before, no bedrock of space or time. In the beginning of our scientific story, there is a similar mystery. The equations of physics whisper that time and space themselves began in a stupendous moment, leaving no trace of a prior era for us to read. If there was a before, it lies hidden behind a veil we cannot yet lift. One idea is that time itself began with the birth of the universe. Asking what came before might be as meaningless as asking what lies north of the North Pole. Another idea suggests our universe is one cycle in an eternal series, that the silence before the Big Bang was the echo of an earlier cosmos that ended, and from its demise, our own was born. In this view, nothingness might be more like a cosmic pause between breaths, the universe exhaling and inhaling over infinite eons. But these are speculations at the edge of knowledge. What we know is that roughly 13.8 billion years ago, the silence ended. Out of the void, a flash of creation erupted. In an immeasurable fraction of a second, the universe began. It burst forth from perhaps an infinitesimal point, smaller than an atom, with unfathomable energy. All the matter, energy, space, and time that now exists was concentrated in that embryonic cosmos. The nothingness, whatever it truly was, gave way to a fierce and blazing emergence. The universe was born from nothing in the sense that no pre-existing space cradled it. It made its own space, it made its own time. That first moment was not a normal explosion in space. It was an explosion of space itself. Silence was replaced by a roar of creation, though there were not yet ears or air to carry sound. Darkness was replaced by a searing burst of light, though in truth, the infant universe was so hot that light was immediately trapped, tangled with matter. Still, we speak in metaphors because our minds need them. We imagine a great cosmic dawn breaking over an infinite expanse of nothing, heralding the start of everything. In reality, that dawn was everywhere at once, and the expanse itself was just coming into existence. From absolute silence and emptiness came a thunderous birth. In the first instance, the universe was a tempest of unimaginable energy. Time and space had just unfurled, and everything that would ever be was compressed into an inconceivably dense state. The temperature was so high that the known laws of physics melded together. Forces that today are distinct, gravity, electromagnetism, the forces that bind atomic nuclei, were unified in that newborn moment. There were no atoms, no particles as we know them, only a furious blur of pure energy. Then, in a brief flash of less than a trillionth of a second, something extraordinary happened. The universe underwent a growth spurt unlike anything since. We call this moment cosmic inflation. It may have been triggered when one of the fundamental forces, the strong nuclear force, snapped free from an earlier unified state, releasing an enormous energy that drove space to expand exponentially. Space itself expanded at a staggering rate, far faster than the speed of light. This did not violate any cosmic speed limit. Rather, It was space carrying matter along, stretching the very fabric of reality. In that infinitesimal blink, the universe grew from smaller than a subatomic particle to perhaps the size of a grapefruit or larger. To an outside observer, if one could exist, it would have looked like nothing one moment and an entire nascent universe the next. But there was no outside yet, for space itself was young and expanding. Why did inflation occur? What drove this wild expansion? These questions remain on the cutting edge of cosmology. Perhaps an exotic form of energy in the vacuum triggered it. A high-energy state of empty space that suddenly released its energy into the expansion of space. As inflation raged, it ironed out any irregularities. Just as a balloon, when blown up, smooths out its wrinkles, the inflating cosmos became extremely uniform. Any curvature or clumps were stretched thin. Distant regions that could never have contacted each other under normal expansion were, just moments before, intimately close together. Inflation flung them far apart, bestowing the universe with vast size and an almost featureless consistency. Almost, but not entirely featureless. Even in the raging furnace of the very early universe, randomness played its part. The quantum world, with its jittery, unpredictable fluctuations, left faint imprints on the density of that primordial energy. Tiny flickers, slight differences in density and temperature originating from the quantum foam of existence, were trapped and amplified by inflation. As space ballooned, those minuscule fluctuations were stretched to astronomical scales. Where there was ever so slightly more energy in the microscopic chaos, now there was a denser patch of universe. Where there was slightly less, a thinner patch. These differences were unimaginably small, mere 1 part in 100,000 deviations from perfect uniformity. Yet they were profoundly important. In time, those tiny wrinkles in the otherwise smooth cosmos would grow into galaxies, clusters, and great cosmic structures. In essence, cosmic inflation took quantum whispers and made them the blueprint for the stars and galaxies we see today. The inflationary burst was over almost as soon as it began, a fleeting cosmic heartbeat of expansion. When it ended, the energy driving it did not simply vanish. Instead, like a wound-up spring suddenly released, that energy transformed into an immense bloom of particles and radiation. The universe reheated. In that moment, what we typically think of as the Big Bang, a hot, dense explosion of matter and light, occurred. Space became filled with a high-energy plasma, a hot soup of particles. In that newborn fireball, matter and energy were interconvertible. Particles were created and destroyed incessantly. Quarks, electrons, antiquarks, positrons, photons, neutrinos, all kinds of exotic, fleeting particles roiled in a searing broth. Protons and neutrons did not yet exist as bound states. Instead, their constituents, quarks and gluons, swarmed freely. The temperature was on the order of billions upon billions of degrees. Matter and antimatter were being forged in almost equal measure, only to annihilate back into light. For every billion matter-antimatter pairs that annihilated, a tiny bit of matter, perhaps one particle, survived without a partner. That vanishingly small excess of matter was enough to ensure that our universe would not end up empty. It would become the stuff of stars and life. The universe almost became nothing again through mutual destruction, but thanks to that slight imbalance favoring matter, something remained. A few grains of matter per immense volume of energy, the seeds from which all galaxies, stars, and planets would later form. As fractions of a second turned into whole seconds, the universe continued to expand, though at a gentler pace than inflation's mad rush. With expansion came cooling. By the time the universe was 1 second old, it had cooled to billions of degrees and was still filled with a dense plasma of particles and radiation. In that first second, the basic forces of nature settled into their separate identities. Gravity had split off earliest, during inflation. Now the strong nuclear force and electro-weak force had also separated into the forces we know today: strong, weak, electromagnetic. The stage was set for the next steps in cosmic evolution. Amid this churning plasma, something else important happened in those first seconds. Neutrinos, ghostly, nearly non-interacting particles, decoupled. These wisps slipped out of the dense throng and began streaming freely through space, barely impeded by matter. The universe became transparent to neutrinos almost immediately, at around 1 second old. Those neutrinos still travel today as an all-pervasive cosmic neutrino background, a silent kin to the light that would later be set free. They are hard to detect, but they remain one of the surviving whispers of the infant universe. The embryo universe, still less than a minute old, was immensely hot and bright. Quarks had begun to combine into triplets, forming the first protons and neutrons within the first millionth of a second, once the universe cooled below roughly 1 trillion degrees. Now, as time passed the mark of a few seconds, the frenetic particle-antiparticle annihilation ended. Most antimatter had paired off and disappeared in a flash of gamma rays, leaving that tiny surplus of matter. A sea of photons, light particles, dominated the energy content, but there were also countless neutrinos, and a growing number of protons, neutrons, and electrons, the raw ingredients of atoms, though not yet assembled into atoms. As the newborn universe moved from its first seconds into its first minutes, it continued to cool and expand. The frenetic collisions of particles began to slow just enough for new kinds of order to emerge. Around 3 to 4 minutes after the bang, the temperature fell to about 1 billion degrees, roughly 70 times hotter than the core of the Sun. Now atomic nuclei could begin to form. Protons and neutrons, freshly forged from quarks, found the universe cool enough to stick together under the embrace of the strong nuclear force. A second great creation event unfolded in this period. Big Bang nucleosynthesis, the formation of the first atomic nuclei. In the blazing furnace of these early minutes, protons slammed into neutrons and fused. Helium, the second simplest element, began to form in abundance. For a brief window of time, conditions were just right for nuclear fusion on a cosmic scale. Much as the cores of stars billions of years later would fuse hydrogen into helium, the entire young universe functioned like a star, converting the simplest elements into slightly heavier ones. Over about 17 minutes, most of the neutrons in the universe, which are unstable on their own and would decay if left isolated, managed to fuse into helium nuclei, each consisting of 2 protons and 2 neutrons, or a few other light nuclei. By the time this period ended, about 25% of the mass of ordinary matter had become helium nuclei, with the remaining 75% remaining as hydrogen nuclei, single protons. A trace of deuterium, heavy hydrogen, and lithium, with 3 protons, also formed. The universe's initial chemical makeup was set: predominantly hydrogen, a healthy dose of helium, and tiny traces of lithium and beryllium. After about 20 minutes, it had expanded and cooled too much for further fusion. The furnace of the Big Bang's beginning flickered out. At this point, the universe was still an extremely hot plasma. Imagine an extremely dense, opaque fog of charged particles, electrons, nuclei, and photons. It was as bright as the interior of a star, but no light could travel very far. Space was like a brilliant, blinding mist. Any photon, particle of light, that tried to go more than a tiny distance would smack into a free electron and scatter. The universe was opaque, a glowing fog of light and matter tightly coupled. To an imaginary observer floating at, say, 100,000 years after the bang, the surroundings would look like a uniform glow, as if you were embedded in the surface of a star. You wouldn't be able to see through it. The concept of distance beyond a certain point had no visual meaning because light hadn't yet broken free. The cosmos was radiating, but curtained by its own dense matter. However, the expansion continued, and with it came cooling and thinning of that particle soup. Thousands of years passed, then tens of thousands. During this epoch, the energy of the universe was dominated by radiation, light, which kept matter particles flying apart and resisted gravity's efforts to clump things together. But gravity was patiently tugging on the matter nonetheless, and as the universe grew, the density of radiation fell faster than the density of matter. About 50,000 years in, matter took over as the dominant component controlling the dynamics of the universe's expansion. The radiation era gave way to the matter era. This meant that at large scales, gravity now had the upper hand to start drawing matter together into the seeds of galaxies and clusters, though it would still be some time before these structures became pronounced, since everything was still mixed in the hot plasma. Fast forward to approximately 380,000 years after the Big Bang. The temperature had fallen to around 3000 K, about the surface temperature of a cool star, roughly an orange glow. At this point, something profound occurred. Electrons began to combine with nuclei to form neutral atoms. A proton capturing an electron makes a hydrogen atom. Helium nuclei capturing electrons make helium atoms. This process is called recombination, though it's really combination for the first time. With most electrons suddenly bound into atoms, they were no longer free to scatter photons at every turn. The cosmic fog lifted. The universe became transparent. It was as dramatic as night turning into day on a cosmic scale, except here it was a bright, hot fog turning into clear darkness. For the first time, light could travel great distances without being immediately absorbed or deflected. When the cosmic fog cleared, the light that had been trapped was released to fly freely through space. The universe was about 380,000 years old, and this was its first free streaming light, often called the first light of the cosmos. The entire sky, everywhere, would have glowed with a bright, warm radiance. If human eyes had existed then and could survive the conditions, they would have seen a soft, orange-white glow coming from all directions, like being in the middle of a vast glowing cloud. That glow was the combined light of the hot plasma, suddenly unleashed. As the universe expanded over time, this flash of light lost energy and shifted to longer wavelengths. What started as an intense orange-white glow stretched into a dimmer red, then into the infrared, and eventually, over billions of years, into the microwave part of the spectrum. Today, we detect this primordial light as the cosmic microwave background, CMB, a faint afterglow permeating the entire universe. The CMB is the oldest light we can see, a messenger from the cosmic infant years. It is extraordinarily uniform, with a temperature of about 2.725 K, just 2.7 degrees above absolute zero in every direction. Yet, it's not perfectly uniform. There are tiny variations in its temperature, only tens of microkelvins different, 1 part in 100,000 of difference. These subtle freckles in the CMB are the direct imprints of the quantum fluctuations from the time of inflation, imprinted on the matter distribution when the universe was young. Regions that are a hair hotter in the CMB correspond to slightly denser areas back then. Slightly cooler spots correspond to slightly less dense areas. These differences are only a fraction of a percent, but they are crucial. Over time, gravity will amplify those slight over- and under-densities into the cosmic structures we see today. When we map the CMB, as satellites like COBE, WMAP, and Planck have done, we are effectively seeing the seeds of galaxies and clusters, the universe's baby picture, with a mottling of warm and cool spots encoding the initial blueprint of cosmic structure. So at 380,000 years old, the universe has become a relatively cool 3000 K neutral hydrogen and helium gas, filling space almost uniformly, and it's transparent. The brilliant youthful glow has now faded into a dull red warmth, and then beyond visible light entirely. What followed is a period often poetically called the Cosmic Dark Ages. Why dark? Because now, with the primordial glow gone, there were as yet no stars or galaxies shining. The universe was transparent and dark. The gas was cooling. The light from the Big Bang was drifting outward, and redshifting into invisibility, and space was largely unilluminated, save perhaps for very faint glows from atomic transitions or cooling gas. Nothing like the bright lights of stars. An observer floating at, say, 100 million years after the Big Bang would see a black sky. The temperature of the background radiation would be a few tens of Kelvin, so mostly microwave radio waves, nothing to see with eyes. Yet all around, gravity was quietly working on the slightly denser patches of gas, drawing them inwards. Gas was not perfectly uniform throughout the universe. Those cooler, slightly denser regions of the primordial gas, the ones corresponding to slightly cooler spots in the CMB, exerted a bit more gravitational pull. They began to gather more gas from their surroundings. Invisible clumps of dark matter, more on this mysterious component soon, were also drawing gas into their deep potential wells. During these dark ages, the universe was like a calm night where nothing visible happens, but seeds are germinating under the soil. Gravity amplified the tiny variations, slowly but surely, pulling hydrogen and helium into ever-growing clouds and filaments. The distribution of matter started to resemble a spider web, dense nodes connected by filaments, with voids in between, though at this early time it was all still diffuse and no stars had lit up. After perhaps a few tens of millions of years, the largest of these gas clouds, particularly where the invisible dark matter had clustered strongly, grew dense enough at their cores to trigger a new phenomenon. The gas at the center of such a cloud, pulled in by gravity, began to heat up as it fell inward. Kinetic energy of infall converted to thermal energy. Eventually, one critical cloud crossed a threshold. Its core reached temperatures of millions of degrees and high pressure. Nuclear fusion ignited. A huge burst of energy was released from the core, and a delicate balance was struck between gravity and pressure. A star was born, the first star in the universe. In pockets across the cosmos, this process repeated. Wherever a pocket of gas became dense and hot enough, a new star lit up. The first stars were likely very massive, dozens or hundreds of times the mass of our Sun, because without heavier elements, like carbon or oxygen in the gas, it couldn't cool as efficiently, and thus fragments of collapsing gas clouds tended to be large. These first stars burned a bright blue-white, extraordinarily luminous, and very short-lived by stellar standards. One by one, like brilliant blue-white beacons, they pierced the cosmic dark. It was as if the universe saw the light of its first campfires, kindling in a vast, cold wilderness, points of illumination sparking up in the blackness. The era of rionization had begun. Each first star flooded its neighborhood with energetic ultraviolet photons. These photons had the power to ionize neutral hydrogen, that is, to knock electrons off atoms. The neutral gas around each new star became electrically charged, ionized, once again, forming bubbles of plasma amidst the neutral background. Initially, these ionized bubbles were small, centered on individual stars or star clusters. But massive stars live briefly. In a few million years, many of them would have died in violent supernova explosions, enriching the surrounding gas with heavier elements like carbon, oxygen, and iron. New stars were born in those same regions, some a bit smaller and longer lived, thanks to the cooling effect of the newly introduced heavy elements. Over several hundred million years, more and more stars formed, and the ionized bubbles around clusters of stars grew and merged. As the first generation of stars grouped into the first proto-galaxies, their combined ultraviolet glow carved out ever-expanding cavities of ionized gas. Imagine the once neutral universe now being Swiss cheesed by growing holes of ionization. Finally, by around 1 billion years after the Big Bang, nearly all the remaining hydrogen in intergalactic space was ionized again. The universe became transparent to ultraviolet light as well, as the last fog of neutral hydrogen was banished from intergalactic space. The Dark Ages had fully ended. The universe was filled with starlight. During this epoch, the cosmic landscape transformed rapidly. Gravity pulled the early star clusters into tighter groups. These groups merged to form nascent galaxies. The first galaxies were smaller and more irregular than the grand spirals and ellipticals we see today. They often were chaotic assemblages of stars, blazing with the light of massive new stars and the explosions of supernovae. Over time, small proto-galaxies merged to form larger ones. The cosmic web, the large-scale structure of matter, became more pronounced. Filaments of dark matter and gas channeled material into the growing galaxies, while vast voids were emptied of matter as it flowed towards the filaments. Some of the early massive stars likely collapsed into black holes after they died. These could have become seeds for the supermassive black holes we find in galaxy centers today. Indeed, by as early as 700 million years after the Big Bang, we have evidence from quasars observed by telescopes that some black holes of billion solar mass scale had already formed and were devouring matter, shining as intensely luminous quasars. That indicates the assembly of galaxies and black holes was well underway very early. In those first billion years, the universe went from a dark, uniform fog to a web of glowing galaxies. It was a dramatic transformation, a kind of cosmic adolescence full of growth spurts and turbulence. Over the next several billion years, this web of structure became ever more complex and beautiful. Gravity and time together sculpted an immense cosmic architecture. Galaxies gathered into groups and clusters, and those clusters themselves drew together into larger complexes called superclusters. On the grandest scales, matter arranged itself in filaments and sheets, weaving around enormous voids. This pattern is the cosmic web. The web forms as the gravitational attraction of matter draws things together along the path of slight initial overdensities. Galaxies are not scattered randomly. They lie along these filaments. Where filaments intersect, we get clusters and superclusters of galaxies, immense nodes of the web. In between lie voids, vast regions with far fewer galaxies, as if the web's threads outline bubbles of nearly empty space. To visualize the cosmic web, imagine looking at a frothy foam or a network of neurons in a brain. Clusters and superclusters are like the knots, filaments like the threads between, and voids like the empty gaps. One filament can stretch hundreds of millions of light years from end to end. Observations have revealed structures such as the Sloan Great Wall and others that span over 1 billion light years. Chains of galaxy clusters lining up. The largest structures known, great walls of galaxies, huge quasar groupings, approach scales where the word structure itself starts to blur, because on scales above a few billion light years, the universe looks homogeneous. Still, these enormous formations amaze us. For instance, one huge grouping of galaxies called the Bootes supervoid, though it's a void, is so large and empty that if galaxies were peas scattered across space, it would be like an expanse, tens of millions of kilometers with only a handful of peas. It's a tremendous volume of space with hardly any galaxies at all, akin to a great cosmic cavern. Within the filaments, galaxies continue to interact. Galaxy clusters, collections of hundreds or thousands of galaxies bound by gravity, form at filament intersections. Our own galaxy, the Milky Way, is part of a small cluster or group called the local group, which in turn sits on the outskirts of the Virgo supercluster, which itself is part of an even larger structure, often called Laniakea, a supercluster complex spanning 500 million light-years. Our local group contains the Milky Way, Andromeda, and dozens of smaller galaxies. Laniakea, a Hawaiian word meaning immeasurable heaven, includes the Virgo cluster and hundreds of other groups, all flowing within a common gravitational basin. It is just one of many superclusters in the observable universe. Even within our local group, cosmic evolution continues. The Milky Way and the Andromeda galaxy are drifting inexorably toward each other. In about 4 billion years, they will merge, forming a new, larger galaxy. This will be a slow-motion collision. Stars are so far apart that few, if any, stars will hit head-on. But the two galactic disks will distort and blend, likely forming a big, elliptical galaxy with a new structure. Such mergers have happened countless times in cosmic history, especially in clusters where galaxies are crowded. It's one way galaxies grow and transform. Our own eventual merger is just a small chapter in the long story of structure formation, but it highlights that even galaxies themselves are impermanent, ever-changing. The cosmic web forms a sort of scaffolding that cradles everything that exists within the universe. And remarkably, the shiny galaxies we see, the gas, dust, and stars, are only a small fraction of the matter involved in this structure. There is an invisible component called dark matter that outweighs the ordinary matter by about 5-to-1. Dark matter neither emits nor absorbs light, so we don't see it directly, but its gravity betrays its presence. It was dark matter that seeded the cosmic web. During the Dark Ages, dark matter clumped under gravity. It does not interact via light or pressure, so it started collapsing even when normal matter was still a hot plasma. These dark matter clumps served as gravitational wells, pulling in ordinary gas after it became neutral. Without dark matter, the gas alone might have taken much longer to form stars and galaxies, but with it, structure formation was boosted. Every galaxy sits in a cushion of dark matter, a dark halo, much more massive and extended than the galaxy's visible extent. In clusters of galaxies, the combined dark matter of the cluster creates deep potential wells that hold the cluster together. In fact, observations of galaxy clusters in the 20th century first provided evidence of dark matter. Galaxies were moving too fast to be held by visible matter alone. So one can picture the cosmic web as an invisible framework of dark matter, upon which gas settled and cooled to produce galaxies. The luminous matter traces the patterns drawn by dark matter's gravity. By around 5 billion years after the Big Bang, many of the structures we see today were in place. The cosmic web was well established. Galaxies had matured and grouped into clusters and superclusters. Stars had been forming for billions of years in those galaxies. In fact, the peak of star formation in the universe likely occurred around 3 to 4 billion years after the Big Bang, when galaxies were in a star-bursting frenzy. After that peak, star formation gradually declined as the gas reservoirs in galaxies were used up or heated or expelled by various processes. In fact, around this midpoint in cosmic history, the conditions were ripe for planetary systems like our own to form. Generations of earlier stars had enriched the interstellar gas with heavy elements, carbon, iron, oxygen, etc., forged in stars and supernovae. In one typical spiral galaxy, our Milky Way, a cloud of such enriched gas and dust collapsed around 4.6 billion years ago to form a new star, our Sun, and a retinue of planets. This was possible because at least 9 billion years had passed since the Big Bang, allowing multiple cycles of star birth and death to scatter the ingredients for planets. Our Sun lit up in a relatively quiet corner of the Milky Way, and around it formed a system of planets, including Earth. On that young Earth, formed from cosmic dust and the debris of earlier stars, complex chemistry began to brew in its oceans and atmosphere. By a few 100 million years after Earth's formation, life arose, simple at first. Over eons, that life became more complex, leading to creatures that could look up and marvel at the stars. In this way, we humans are very much a product of cosmic evolution. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were forged in long-dead stars and scattered through space, incorporated into the Sun and Earth, and ultimately into us. Our emergence is an exquisite example of the universe giving rise to organized complexity capable of contemplating itself. While this was happening on the scale of galaxies and life, another, even larger scale drama was unfolding in the background, the expansion of the universe itself. Since the Big Bang, the universe has been expanding, but for a long time, It was expected that this expansion should be slowing down due to the pull of gravity. Indeed, for the first few billion years after the Big Bang, the expansion was decelerating. The mutual gravity of all the matter in the cosmos was putting the brakes on the expansion. Galaxies, though being carried apart, were doing so at an ever-slowing rate. One might have imagined that given enough time, the expansion might even stop and reverse if gravity was strong enough. However, about 6 or 7 billion years after the Big Bang, roughly at the time our Sun formed, something curious started to happen. The expansion began to speed up again. Galaxies started to recede from each other faster and faster. This discovery, made by observing distant exploding stars, supernovae, in the late 20th century, was revolutionary. It implied the presence of a new ingredient in the cosmic recipe, something pushing the universe outward. We call this mysterious influence dark energy. Dark energy is the name we give to the unknown cause of the accelerated expansion. It appears to act much like what Einstein once hypothesized as a cosmological constant, an intrinsic energy of empty space. Einstein originally introduced such a term to allow for a static universe, then removed it when expansion was discovered, reportedly calling it his biggest blunder, not realizing the universe actually does have a similar effect present. Dark energy doesn't dilute as the universe expands. It remains, as far as we can tell, constant in density. As space grows, the total amount of this energy increases, because more volume times the constant density yields more energy. In effect, dark energy is like an anti-gravity pressure uniformly filling space, pushing things apart. For the first several billion years, dark energy was negligible compared to matter. Matter's gravity was slowing the expansion. But as matter spread out and its density dropped, dark energy eventually became significant. About 5 billion years ago, dark energy's repulsive effect overtook the self-gravity of matter in the universe. The expansion, which had been slowing, stopped decelerating and began to accelerate. Small distances, like within galaxies or clusters, weren't affected. Those structures are bound by much stronger local gravity. But on large scales, between clusters and superclusters, the gaps began to widen faster and faster. To picture the effect of dark energy, imagine the universe's expansion as a ball that was thrown upward, the Big Bang being the throw. First, the ball climbs, but slows, gravity's pull. Then, unexpectedly, it starts accelerating upward as if pulled by an unseen force. Dark energy is akin to that unseen force accelerating the expansion of the cosmic ball. Another analogy. Think of 2 points in space with a spring between them, gravity, and an expanding rubber sheet under them, space itself expanding. Initially, the spring slows their separation, but if the rubber sheet stretching, dark energy, grows strong enough, it will overcome the spring and the points will fly apart faster and faster. The simplest form of dark energy, consistent with observations, is a true cosmological constant, an unchanging energy woven into the fabric of space-time. If that is the case, then the fate of the universe is a continual acceleration. Distant galaxies will recede at ever-increasing speeds. Eventually, far in the future, distant galaxies currently visible will be carried beyond our horizon of visibility because space is expanding so fast that light from them can no longer reach us. The night sky over tens of billions of years will grow emptier as galaxies vanish from view one by one. Today, dark energy makes up about 68% of the total energy content of the universe. Matter is about 32%, of which about 27% is dark matter and 5% normal matter. Thus, the cosmos, by composition, is mostly this invisible, dark energy. It's astonishing. All the galaxies, stars, gas, and dust, everything we see, is only a trace component. Yet, it is thanks to that small component that we have structure and life. Dark energy, ironically, mostly influences the voids and the eventual destiny. Even now, dark energy's presence is subtle on human timescales. The Milky Way and Andromeda will still collide despite cosmic expansion because they are gravitationally bound strongly enough to overcome expansion at local scales. The local group of galaxies will remain together, but clusters that are not bound to us will drift away. For instance, galaxies in the Virgo cluster, tens of millions of light years away, will recede further. In a few 100 billion years, should any observers be around, virtually all galaxies beyond the local group will have disappeared from view, being carried away faster than light can catch up. To summarize the cosmic inventory and its effect, dark matter provided the scaffold for structure and still holds galaxies and clusters together. Dark energy drives the overall expansion ever faster. Normal matter, atoms, forms the stars, planets, and living beings. Each plays a role in the grand cosmic story. Dark matter pulled the cosmos into a beautiful web. Normal matter lit that web with stars. Dark energy is now pulling the web apart at its largest scales. Time marches forward, and with it comes change. But why does time have a direction at all? We recall the early universe was an extremely hot, uniform state. And now we have a clumpy cosmos and cool expanses. Things have clearly moved from a state of order to increasing disorder. This one-way progress is encapsulated in the concept of entropy. The second law of thermodynamics says entropy, disorder, tends to increase in a closed system. This law underpins the arrow of time. Eggs break, but do not unbreak. Cream disperses in coffee, but never spontaneously gathers back at the top. A piece of paper burns to ash and smoke, but the ash and smoke won't reconstitute into paper on their own. These processes involve increasing entropy, and they define an irreversible direction to time, from past, lower entropy, to future, higher entropy. The universe as a whole began in a state of incredibly low entropy. At the moment after the Big Bang's initial inflationary smoothing, matter and radiation were almost perfectly uniformly spread. Paradoxically, uniform gas is a low entropy state in cosmology because gravity can do a lot of work with it. Imagine a smooth spread of matter that can clump versus matter already clumped into black holes. The latter is a higher entropy state gravitationally. The early universe had very low gravitational entropy, everything spread out smoothly, and not maximal thermodynamic entropy either. There were temperature differences and lots of free energy available. This special beginning, perhaps set by inflation or whatever preceded it, is why there was an arrow of time. The cosmos started wound up, like a clock with a lot of free energy and potential to evolve into more disordered states. As the universe aged, entropy increased. The formation of stars and galaxies might seem like an increase in order locally, but overall, entropy rose because, for example, when a star shines, it produces a lot of thermal radiation, high entropy, out of nuclear fuel, lower entropy state. The light that escapes into space carries away entropy. The net effect of all processes, gravitational clustering, star formation, life, has been to increase total entropy. Entropy is now vastly higher than in the pristine early universe, and it will continue to increase. What is the ultimate fate implied by ever-increasing entropy? It is often called the heat death or big freeze. This scenario is a universe where, on the largest scales, everything becomes uniform again. Not in a low entropy way like the beginning, but in a maximum entropy way. A thin mist of particles and radiation at near uniform temperature, with no gradients to power any process. If dark energy continues to accelerate expansion forever and nothing intervenes, this is the likely end state trillions upon trillions of years hence. Let's trace that future vision. First, over the next few trillion years, star formation in galaxies will taper off. Galaxies have a finite supply of gas to make new stars. Eventually, that gas runs out or becomes locked in stellar remnants. The longest-lived stars, small red dwarf stars, can burn for trillions of years, far longer than the current age of the universe. So, billions of years from now, Galaxies will be dominated by long-lived red stars slowly fusing hydrogen. As time marches on, even these will exhaust their fuel. By around 100 trillion years from now, 10-14 years, the era of star formation will officially end. We enter the so-called degenerate era, dominated by stellar remnants. In that far future, the galaxies, those that remain gravitationally bound, like our future Milkdromeda, the merged Milky Way Andromeda, will be populated only by degenerate objects, white dwarfs, cores of spent stars, neutron stars, brown dwarfs, failed stars, and black holes. New stars will no longer be born. The remaining stars will slowly cool and dim. White dwarfs, starting hot, will radiate their energy over billions and trillions of years, turning into black dwarfs, cold, dark, stellar embers. Planets, if any still orbit, will gradually spiral into their stars or be flung out by gravitational encounters over extremely long timescales. At this point, entropy is still increasing. Complex structures decay. Perhaps some hypothetical, incredibly long-lived civilization might find ways to survive around fading sources of energy, but eventually usable energy supplies would dwindle. After many trillions more years, even larger structures start to destabilize. Gravitational interactions within what's left of galaxies will gradually eject many objects into intergalactic space, a process called dynamical relaxation. Central black holes might collect some matter, while other stars or remnants are thrown to the outskirts or beyond. Fast forward to unimaginably distant times, 1019, 1020, up to 1040 years. By 1020 years, most galaxies as we know them may disperse, stars either fallen into central black holes or scattered. Around 1040 years, a number so large it defies comprehension, even protons, if unstable, some particle theories suggest protons might eventually decay, will have decayed into lighter subatomic particles. If proton decay is real, at this point, solid matter dissolves. Planets, white dwarfs, any remaining asteroids or dust, all would literally evaporate into radiation and elementary particles. The universe becomes a dilute soup of electrons, positrons, neutrinos, and photons, perhaps with some lingering protons if they're absolutely stable, and lots of dark matter particles. Assuming dark matter is stable and doesn't decay, we aren't sure, but likely it is stable. One might think black holes would still be around as massive reservoirs of mass, even after normal matter is gone. And they will, for a long time. But even black holes aren't eternal. Stephen Hawking theorized that black holes slowly evaporate by emitting Hawking radiation, a very slow quantum thermal glow that causes them to lose mass over time. For stellar mass black holes, the evaporation time is around 10^67 to 10 years. For supermassive black holes, millions or billions of solar masses, like in galaxy centers, the time is stupendously larger, on the order of 10^98 to 10^100 years or more. But given enough time, even these giants will eventually evaporate completely, each ending in an explosive burst of high-energy particles when its mass becomes very small. After the last black hole has vanished, the universe enters its final stretch, the dark era. The temperature everywhere will approach an extremely low value as expansion dilutes any remaining energy. Essentially, what remains is a sparse sea of photons, mostly of extremely long wavelength radio waves, some electrons, positrons, neutrinos, and perhaps some dark matter particles if they haven't decayed, all spread so thin that in a volume the size of our Earth, you might find essentially none of those particles. Entropy is maximized. In a sense, the cosmos returns to a featureless state, not of super-hot plasma like the beginning, but of near-empty cold space. All gradients of temperature or density are ironed out. With no free energy differences, no work can be extracted to power any process. Change virtually halts. This is the heat death. Time would still pass, but nothing of significance would mark its passage. It's a ghost universe, silent, empty, and everlasting, unless some fluctuation eventually breaks the stalemate, which we'll touch on. The arrow of time at that point would effectively cease to matter, because there would be no events to distinguish past from future. The great cosmic drama would have quietly exited stage right. However, this fate assumes a constant dark energy and no new physics intervening. We must acknowledge other possibilities. The universe's end might be more dramatic or lead to a rebirth. One such possibility is the Big Rip scenario. If dark energy is not constant, but instead grows in strength, for example, its equation of state has W1, a so-called phantom energy, the acceleration would become more and more violent. Eventually, even gravitationally bound systems would not hold together. In a Big Rip, first clusters of galaxies would be torn apart, galaxies receding from each other despite being bound, effectively overcoming their mutual gravity. Next, galaxies themselves would be shredded, stars flung out as the space within the galaxy expands faster than the galaxy's gravity can keep up. Closer to the rip, solar systems would unbind, planets would fly off from stars. In the final moments, stars and planets would be ripped apart, and even atoms and atomic nuclei would be sundered in the ultimate blow. The timeline for such an event depends on how phantom the dark energy is. If it were just slightly more negative than 1 in its equation of state, the Big Rip might be trillions of years away, or not happen at all, if it tends asymptotically to a constant. If it's substantially more negative, the rip could happen sooner, though current data suggests dark energy is very close to a cosmological constant, W1. The concept is spine-chilling, the fabric of space accelerating so wildly that it rips apart anything bound. Matter is literally disassembled by the expansion of space. Most physicists consider this unlikely based on current evidence, but it's not ruled out absolutely. If our current best fit is slightly off, the cosmos might end not in ice, but in a singular crescendo of tearing apart everything. Another scenario, the Big Crunch. This is in a sense the opposite of heat death or Big Rip. It's a reversal of the expansion into a contraction. If, for some reason, dark energy were to dissipate or turn attractive, and if the density of matter were high enough, gravity would eventually win out and pull everything back together. The expansion would slow, stop, and reverse. Distant galaxies would start to approach rather than recede. Over billions of years, what was once an expanding universe becomes a collapsing universe. Galaxies would rush together. Clusters merge into a supercluster, superclusters into huge sheets, and finally all material closes in. The temperature of the background radiation, which had been dropping for eons, now starts to rise again as space compresses that radiation. The dark, quiet cosmos would light up once more as every particle of light gains energy and blue shifts. Galaxies might careen into each other with increasing frequency. The night sky would glow brighter and brighter as more galaxies cram into our observable view, and the heating of all gas triggers star formation, or makes existing stars shine more fiercely. In the far future of a Big Crunch, the universe's scale continues to shrink. What were galaxy superclusters a few billion years before are now overlapping and colliding. Eventually, all matter might coalesce into an extremely dense state. The temperature would soar to star-like or greater levels everywhere, ionizing whatever atoms existed once more. Fusion could ignite in giant bursts as gas clouds compress. Essentially, the reverse of the universe's expansion timeline happens. Clusters of galaxies collapse into blazing quasars, then into massive nebulae, then into a shrinking ball of plasma, then perhaps into conditions similar to the very early universe. If quantum gravity or other effects don't intervene, this collapse could lead all the way back to a state of seemingly infinite density and temperature. Essentially, a mirror image of the Big Bang, sometimes dubbed the Big Crunch. Is that truly an end, or could it be a bounce? Some modern theories speculate that a Big Crunch could transition into another Big Bang, the death of one universe seeding the birth of a new one. In cyclic models, the universe might undergo endless, or at least many, bang crunch cycles. Ancient cosmologies, like Hindu cosmology, imagined time as cyclical, cosmic days and nights of Brahma, with universes expanding and contracting periodically. A scientific version might be, after a crunch, all space and time re-expand again, maybe after reaching a singularity, or perhaps never fully reaching infinite density because new physics causes a rebound. If there is a bounce, the astonishing implication is that our Big Bang might not have been the absolute beginning, but simply the latest bounce. Some theorists working in quantum cosmology and string theory have explored models where, for example, our 3D universe, brain, periodically collides with another brain, causing big bangs in a cycle. Others, loop quantum cosmology, find that quantum effects could cause space to repel at extremely high densities, avoiding a singularity and starting expansion anew. If the universe can bounce, what happens to entropy and the arrow of time in such a cycle? That's a tough question. Naively, entropy would carry over and increase with each cycle, which would be problematic. You can't cycle indefinitely if entropy irreversibly accumulates, unless the bounce somehow resets the entropy or disposes of it. Some proposals, like conformal cyclic cosmology, Roger Penrose's idea, suggest that at the end of a heat-death scenario, when the universe is nothing but photons and essentially devoid of scales, it might be possible to relabel that state as the initial singularity of a new Big Bang. Since a universe of only structureless photons has no concept of time or size, it could be equivalently reinterpreted as a new Big Bang state. This is speculative and not widely accepted yet, but it shows how creative thinking is being applied to the idea of cosmic rebirth. There are also other theoretical fates. One is a vacuum decay scenario. Perhaps our current vacuum, the ground state of fields in the universe, is not the true lowest energy state. If there exists an even lower state, the universe could at some point quantum tunnel into that lower state. If that happened, a bubble of true vacuum would appear somewhere and then expand at near the speed of light, converting everything it touches into a new state of being. Within that bubble, the laws of physics might be different constants, particle arrangements. So essentially, it's like a new universe erasing the old one. This bubble nucleation and expansion would be catastrophic, from our perspective, and extremely fast. One moment everything's fine, the next, a bubble of alien vacuum is rushing through you, disintegrating you, Earth, and every structure, and we'd never see it coming because it expands at light speed. It's a wild idea, but certain particle physics models make it a possibility. For instance, if the Higgs field sits in a metastable false vacuum. Current data suggests it's not highly likely in the near term. If it can happen, it might be trillions of years away or more. Or maybe it's truly stable and won't happen at all. In any case, it's another way nothing, or rather a different something, could be born from our something, effectively resetting the cosmic stage abruptly. Finally, even in the heat-death scenario, some have mused about the possibility of random fluctuations creating new ordered patches. Given infinite time in a static de Sitter universe, the end state with dark energy domination, quantum fluctuations could occasionally, by sheer chance, produce a small region of lower entropy, perhaps even a new Big Bang seed, or a so-called Boltzmann brain, a spontaneously formed self-aware entity out of chaos. While these ideas are thought experiments and lead to some absurd-sounding consequences that physicists debate, often to argue that an eternal de Sitter phase might be problematic or that some new physics must intervene before infinity, they speak to the richness of considerations about eternity. Even in an endless nothingness, given unlimited time, perhaps a fluctuation might trigger a new creation event. The probability is incredibly low for any given moment, but in infinite time, the unlikely becomes inevitable. So perhaps heat death isn't truly the end. It could be a plateau before another beginning, in an endlessly cyclic multiverse of fluctuations. This is deeply speculative, verging on philosophical, but it shows that even finality might not be absolute. At this juncture, we've painted possible endings: eternal expansion into heat death, a big rip, a big crunch with possible bounce, or a transition to something entirely different. Each path carries different implications for the arrow of time and for the question of whether the universe has a purpose or just a lifespan like any other natural phenomenon. From what we can tell now, with our cosmological measurements, the most likely fate is an ever-accelerating expansion leading to a very cold, very empty universe. Heat, death. But our knowledge is incomplete. Dark energy could surprise us by changing behavior. New physics, like interactions between dark energy and matter, or a slow dilution of dark energy, could alter the story. Now, let's step beyond even these questions of our universe's fate and ask, is our universe the only universe? For much of our narrative, we presumed that the universe meant all that exists. But modern physics has opened the door to the idea of a multiverse, a larger reality in which our universe is just one part. There are actually different notions of multiverse that scientists discuss. One arises from quantum theory, the many worlds. Interpretation suggests that all possible outcomes of quantum events actually occur, each in its own separate branch of reality. In that view, reality continually splits into a vast ensemble of parallel timelines. That's a kind of multiverse, a branching tree of universes coexisting in superspace. It's a very different concept from universes separated by space. It's more like parallel dimensions or alternate histories. It might not affect our cosmic story directly, so let's set that aside after noting it as an intriguing possibility. Parallel universes where, say, different events happened in history, etc., playing out side by side unbeknownst to each other. The multiverse idea, more relevant to cosmology, arises from cosmic inflation and string theory. If inflation occurred as our theories suggest, the ultra-fast expansion in the universe's infancy might not have been a one-time event that ended everywhere at once. There are strong reasons to suspect inflation is eternal. While it ended in our region, allowing our Big Bang fireball to proceed, in other far-flung regions, inflation might still be going on, endlessly creating more bubble universes. Picture a vast, inflating space-time, a kind of ever-growing foam. Occasionally, in that foam, regions stop inflating and crystallize into hot Big Bang bubbles like ours. Each bubble is a universe in its own right, with potentially different properties depending on slight quantum variations when inflation ended there. Our observable universe would be just one bubble that happened to nucleate 13.8 billion years ago. There could be countless others. These other universes are not located in our space. They are separated by continuing inflating space, which expands so fast that we can never catch up to the neighboring bubbles. They are forever out of reach. Each bubble might have different physical constants, particle content, even dimensionality, especially when combined with ideas from string theory. String theory suggests that the vacuum of the universe, the configuration of extra dimensions and fields, could have many possible states, sometimes quoted as 10 to 500 or more possibilities in the landscape of string theory solutions. Each bubble universe could realize one of those many possibilities. That offers a tempting explanation for why our universe has the peculiar laws it does. If there is a multiverse of all kinds of universes, we just happen to be in one that had the right conditions for galaxies, stars, and life, because otherwise we wouldn't be here to observe it. This is a kind of anthropic selection from a multiverse ensemble. It's important to note, none of this multiverse speculation is confirmed, but it is grounded in serious physics theories. Eternal inflation is a rigorous outcome of many inflation models. Once inflation starts, it generically doesn't stop everywhere, so while one bubble forms, inflation continues elsewhere, leading to potentially infinitely many bubble universes. And in string theory, the many possible shapes of extra dimensions, each giving rise to different physical constants, combined with inflation, virtually guarantees a multiverse. The inflating space fills itself with regions realizing all those options. Can we detect or observe evidence of other universes? It's challenging by definition. If they are truly separate, we can't see into them. But one possible sign would be if a neighboring bubble universe in the early inflationary period happened to collide with our bubble. That collision might leave an imprint, perhaps a circular pattern or a particular kind of distortion in the cosmic microwave background. People have actually searched CMB maps for hints of such collisions. So far, none have been convincingly found, but the search exemplifies how we don't shy away from trying to test even outrageous-sounding ideas. Another hint could come from the distribution of gravitational waves or subtle effects on the distribution of galaxies, none detected yet in a way that screams other universe. Another multiverse notion comes from higher dimensions and brain-world scenarios. String theory requires extra spatial dimensions, 6 or 7 beyond our usual 3. Those dimensions could be compactified, curled up small, or in some models, we could be confined to a 3D brain floating in a higher dimensional space. There could be other brains, essentially other universes, separated from ours in the extra dimensions. Normally, we'd have no interaction with them except perhaps gravity, which can propagate in the higher dimensional bulk. Some have even imagined that a collision between brains could be what the Big Bang was. 2 3D worlds collided, releasing energy that flooded our brain with the hot matter of a Big Bang. If those other brains, universes, exist, they are right next door, in a sense, perhaps only a tiny distance away in a 4th spatial dimension. But we can't see them or touch them because our particles and light are confined to our own brain. It's a mind-bending concept. Other entire universes, potentially a millimeter away from us, in a direction we can't perceive. Whether it's bubble universes, parallel quantum worlds, or higher dimensional brain worlds, the multiverse idea profoundly changes the context of our cosmic story. Our universe could be a small chapter in an infinitely larger ensemble. It could mean that what we consider the ultimate beginning, the Big Bang, is just one local event in an eternally evolving multiverse. And it forces interesting questions. If there are countless universes, each with possibly different physics, what does that say about meaning? One could imagine each universe as having its own narrative, its own potential for life, or even intelligence. Are there other conscious beings out there, not just in our universe, perhaps in distant galaxies, but in entirely separate universes, forever causally disconnected from us? This drifts from science into philosophical wonder, because by construction, we may never verify those other universes. Yet, the theories that predict them, inflation, quantum mechanics, string theory, are in principle testable in other ways and have earned credibility. So we take the multiverse seriously, while acknowledging it currently lies at the speculative frontier. Regardless of whether there's a multiverse, we find ourselves in this universe with its particular story. From a singular beginning, or at least an extremely hot, dense early state, our universe expanded, cooled, formed structures, and eventually produced us, beings capable of reflecting on the whole process. We've gone from contemplating mythic cosmologies to actually measuring the geometry and expansion history of the cosmos. We discovered the universe had a beginning, Big Bang, that it is 13.8 billion years old, that it expands, that it has a cosmic web of structure, and that it is dominated by dark matter and dark energy. These are incredible revelations, won through the hard work of observation and theory, building on generations of curious minds. Now we turn to the philosophical and existential implications of the cosmic story. Standing under the night sky, we can feel 2 seemingly opposite emotions: insignificance and profound connection. On one hand, the universe is vast beyond imagination. The Earth is a tiny pebble in a gigantic space. Even our galaxy, with 100 billion stars, is just one in a sea of billions of galaxies. Physically, We occupy no privileged position. The cosmos is not arrayed with humanity at the center. We are off in a corner of an average galaxy, which itself is in a supercluster that is unexceptional among others. Time-wise, human history is an eye blink compared to cosmic time. The stars shone for billions of years before we came along. They will continue billions of years after we are gone. It's humbling, even daunting, to recognize this. The famous pale blue dot photograph taken by Voyager 1 from beyond Pluto, showing Earth as a tiny bluish speck in the void, encapsulates that humility. All of human history, every joy and sorrow, every hero and villain, played out on that mote of dust, suspended in a sunbeam in the vast darkness. When confronted with such scale, it's natural to feel small. Yet, on the other hand, how marvelous that we can comprehend this scale. We are made of particles that were forged in stars. Essentially, the universe gave birth to conscious organisms that can observe and contemplate the universe. We are a way for the cosmos to know itself, a sentiment popularized by Carl Sagan and profoundly true. Our atoms originated in the Big Bang, hydrogen, or in stellar furnaces, carbon, oxygen, nitrogen, etc., or in supernovae, iron, zinc, iodine, gold, all the heavier elements. We are literally children of the stars, made of stardust. Through us, the materials of the universe have become aware and curious. That imbues us, and possibly other intelligent life out there, if it exists, with a kind of cosmic significance, albeit a self-bestowed one. We carry the legacy of 13.8 billion years of cosmic evolution in our bodies. When we gaze out at the galaxies, those galaxies are in a sense observing themselves through our eyes. The emptiness of space, while vast, is not completely empty. It's filled with fields and particles and possibilities. Likewise, the perceived emptiness or pointlessness one might feel when confronted with a giant, cold universe can be filled with our own meaning and purpose. The cosmos doesn't hand us a script. Instead, it gives us the stage, the raw materials, and the invitation to create meaning. And humans have been doing that for as long as we have existed, through story, science, art, love, and exploration. We find that the more we learn about the universe, the more beautiful it becomes. Consider the fact that the atoms in your body were once inside of a star, perhaps many different stars over the eons. In a very real sense, you are as old as the universe, because the matter that composes you has been around since the beginning, apart from some recent transmutations via nuclear reactions. We are deeply connected to the cosmos. Every breath you take contains atoms from all over Earth and beyond, even some noble gas atoms that were forged in the Big Bang. The water you drink contains hydrogen made at the dawn of time. The calcium in your bones was fused in some star that ended its life long before Earth formed. We are a microcosm of the universe. This perspective can evoke a sense of spiritual awe, even in a non-religious framework. It's the awe of existence itself, the recognition that we are part of something vast and magnificent. The American astronomer Harlow Shapley said, "We are akin to the totality of things. The atoms don't belong to us, we belong to them. We are a moment in their journey." The universe's story also imparts lessons. One is the transient nature of all things. Stars are born and die. Even galaxies collide and merge. The universe evolves. Change is the rule. On Earth, we see that civilizations rise and fall, species come and go, all part of that cosmic change. But amidst change, there is continuity. The continuity of matter and energy, and the continuity of information passed on. Our sun inherited matter from previous stars. We inherited molecules from Earth's past life. We pass our atoms back to the Earth when we die. It's a kind of immortality, not personal immortality, but the persistence of our substance and our influence. A star that died billions of years ago in our region of the galaxy, by dying, it seeded the cloud that formed our solar system. In a way, that star lives on through us. Likewise, the choices we make and the knowledge we gain might propagate far into the future, indirectly shaping things we will never see. When we build a telescope and discover something, that knowledge changes the consciousness of humanity, which may alter our future actions and fate. Our cosmic understanding has also, interestingly, circled back to some ancient wisdom. Many cultures intuited a connectedness of all things, or a cycle of creation. The scientific specifics we've learned differ from the myths. The universe isn't literally the egg of a giant bird, for instance, but the emotional thrust that we are part of a greater whole is affirmed more strongly than ever by science. We now see that the same physical laws apply everywhere. We've sent probes to other planets and found familiar chemical processes at work. We've detected light from atoms in distant galaxies and found the same spectral lines as atoms we study in labs. The universe has a unity, and the story of cosmic evolution is a single, continuous narrative from the Big Bang to the present and onward to possible futures. We are a chapter in that narrative. In contemplating the end scenarios like heat death or Big Rip, one can feel despair. Will it all amount to nothing? But one might also find liberation in it. The distant future is beyond our control. What matters is what we do with the time and universe we have. The fact that the universe will end in one way or another does not negate the preciousness of its present. In fact, it enhances it. Just as mortal beings find meaning in life partly because it is finite, the finite window of a lively universe can galvanize us to appreciate its wonders all the more. We live in a cosmic springtime, when conditions are just right for complexity and life. It will not always be so, but how fortunate that it is so now, and that we are here to witness it. There's also a school of thought that even if our universe fades, perhaps life, or an advanced form of intelligence, could in some way continue or influence beyond its own universe. Some speculative ideas suggest extremely advanced beings might even hop between universes or create baby universes artificially. These ideas blur science and philosophy and remain in the realm of imagination for now. But the mere consideration expands our sense of possibility. Perhaps the end of the universe isn't an absolute wall, but just another frontier to transcend for a sufficiently ingenious civilization. It sounds like science fiction, and it certainly is right now, but who can definitively say what a Type 3 or Type 4 civilization, if it could exist, might achieve after millions or billions of years of evolution? Bringing our thoughts back to the here and now, the night sky. It connects us to all of this grand history and future. When you next stand under the stars on a clear night, think about the journey of a photon that enters your eye. Perhaps it left a distant galaxy when that galaxy was young and our planet not yet formed, traveling across expanding space for tens of millions of years, through voids and past clusters, until finally, one night, it ended its journey on your retina, triggering a chemical reaction that led to an image in your brain. In that moment, you, a being of stardust, assembled on an 8-planet minor system around an unremarkable star, catch a whisper from the other side of the universe. And with collective effort, humanity has learned to interpret these whispers, to tell a coherent story of how we came to be. The cosmos is mysterious and beautiful. Every discovery seems to open new questions. We determined the age and shape of the universe, only to find most of its content is invisible, dark matter and dark energy. We may solve dark matter, perhaps a type of particle, and dark energy might remain puzzling or turn out to be a property of space itself. We look for potentially habitable exoplanets, wondering if life arose elsewhere. We tune our radios for possible signals from other civilizations, not knowing if we are alone or one of many. We delve into the quantum foam, attempting to reconcile general relativity, our theory of the very large, with quantum mechanics, the theory of the very small, hoping for a deeper understanding that might unify forces or reveal why the Big Bang happened the way it did. The quest goes on. Through it all, there is a human element that persists: wonder. As the astronomer Maria Mitchell said, "We reach forth and strain every nerve, but we seize only a bit of the curtain that hides the infinite from us." Yet, that bit of curtain has revealed an awful lot, and we continue to gently pull at it. Will we ever see the infinite, or the true beginning, or the full scope of the multiverse? Perhaps not, but the pursuit is part of what makes us human. The same impulse that made our ancestors paint constellations on cave walls and craft stories of creation now drives rockets and equations toward the heavens. Ultimately, the story of the cosmos is meaningful to us because it is also our story. We are not mere spectators. We emerged from this grand process. The hydrogen in our bodies, in every molecule of water, for instance, comes straight from the Big Bang. That means a part of us is as old as time. The carbon in our cells was forged in stellar hearts, making us the heirs of those stars. When we die, our atoms will return to the Earth, and eventually some will drift out to space again, maybe to become part of a new star or planet eons hence. In that sense, we are immortal, though our forms are temporary. So, what does it mean to be born from nothing? It means that existence is a gift against all odds, a tiny realm of something in an infinite sea of nothing. It means that perhaps nothing is unstable or pregnant with potential, that even a void can give rise to worlds. It suggests that reality is not a static block, but a dynamic story. Our universe began in a state devoid of structure, grew into a vast living tapestry, and will either continue to expand and evolve in complexity for some time, or eventually simplify again into quiescence. We got to observe a rich segment of that timeline, full of galaxies and life. That realization can fill one with a sense of reverence, not in a religious sense, but a profound respect for the majesty of nature. As our journey through the cosmos comes to an end, let's reflect on where we are. A small planet orbiting a medium star, on the edge of a galaxy that has at least 100 billion siblings, in a universe of maybe 2 trillion galaxies within our view, each brimming with stars and possibilities, all governed by the same physical laws, all born together in the same primordial explosion, all fated to either drift apart forever or perhaps crash together in some finale. We, ephemeral yet remarkable, stand here and through ingenuity have uncovered this story. It is a continuous, cinematic, emotionally resonant story, one that stretches from the beginning of time to the very ends of imagination. It's a story told by starlight and cosmic background whispers, written in equations and in the awe of anyone who looks up at the midnight sky. It's the story of the cosmos, our story. And though this particular telling of it must now conclude, the story itself goes on, written in the galaxies overhead and the atoms within us. As long as there are thinking beings to wonder and explore, the narrative will be retold, refined and cherished anew. In that sense, the cosmic story truly has no end. It lives so long as curiosity lives. So take a moment to step outside on a clear night. Feel the cool air. Look up. The light hitting your eyes has traversed the universe to reach you. The atoms in your body resonate with the history of the cosmos. The void may be vast, but you carry within you a universe of understanding that fills it with meaning. In the silence of the night, you can hear, if you listen closely, the echoes of the Big Bang and the songs of ancient starlight. The story of everything is speaking, and through our minds and hearts, the cosmos is listening to its own tale. In that communion, between the cosmos and our consciousness, lies a profound truth, that we are not apart from the universe. We are the universe, in small but significant part, and its fate and our fate are intertwined. From nothing we came, into nothing, or something beyond, we may go. But in between, we have the chance to witness and marvel at the grandest of spectacles, existence itself. Let us be grateful for that chance. Let us keep the cosmic perspective, allowing it to illuminate our lives with both humility and wonder. And let us continue the journey, always, for as far as mind and imagination can reach, embracing the mystery and majesty of the cosmos. The cosmic saga continues, and we are fortunate narrators within it. The final line is not yet written. The night is dark and vast, an ancient canvas of silence spangled with stars. Then, without warning, a new light pierces the sky. A soft glow emerges just above the horizon, growing into a brilliant streak that arches across the darkness. It is a comet, sudden, bright, ancient, beyond measure. The sight catches your breath. There is something primeval in this glowing apparition, as if a piece of the dawn of the cosmos has come visiting. It hangs like a celestial torch, its tail a shimmering train of pale light. In that moment of discovery, under that cosmic beacon, you feel the pull of both wonder and reverence. Time seems to slow as the comet's tail unfurls across the stars, a ghostly plume etched in the night. Standing there, you are not merely an observer, you are a participant in an age-old human story of awe. Thousands of years ago, someone like you looked up at such a sight with trembling heart, wondering what it meant. Was it a herald of doom, a dragon of the skies, or a divine messenger? Myths sprang from moments like this. A dragon's fiery breath, a sorcerer's wand, a weeping ghost of a long-dead star. Even knowing the science, you can feel those old echoes. A comet ignites the imagination. Its beauty is laced with a whisper of terror from our ancestors' memories. But armed with understanding, awe overtakes fear. You stand in quiet excitement, aware that you are witnessing a traveler that may have last passed this way when civilizations were young. What exactly is this cosmic wanderer that paints the sky? To the naked eye, it looks like a star with a wispy tail, but in truth it is something far more intricate. At the heart of the spectacle is the comet's nucleus, a small, solid core, often just a few kilometers across. You cannot see it from Earth, but hidden in the comet's brilliance is that nucleus, a dark, irregular lump of ice and dust, like a frozen capsule of time. As the comet drew nearer to the sun on its long journey, the warmth began to awaken it. Ice locked away for eons began to sublimate directly into gas, jetting out from the nucleus and dragging dust with it. This activity created a fuzzy, luminous cloud around the nucleus, known as the coma. The coma is what gives the comet that hazy star-like head, a diffuse sphere of gas and dust that can swell to tens of thousands of kilometers across, enveloping the nucleus in a glowing shroud. The sunlight and the solar wind, those incessant streams of charged particles blowing outward from the sun, grab hold of the coma and sculpt it into the comet's magnificent tail. In fact, the comet wears not just one tail but often two, one of dust and one of ionized gas. The dust tail, formed by tiny grains pushed gently by the pressure of sunlight, shines with the reflected light of the sun. It often appears curving and broad, a fan of golden white that traces the comet's recent path. The ion tail, made of gases that have been ionized, electrically charged, by solar ultraviolet light, is caught up and carried straight outward by magnetic fields in the solar wind. This tail is usually narrow and straight, often tinted blue from glowing carbon monoxide ions. It points directly away from the sun, a taut streamer of plasma connecting the comet to our star's influence. Tonight, under your gaze, the dust tail of our comet sweeps upward, slightly arched, while a fainter bluish filament, the ion tail, points off in another direction, straight as an arrow away from the sunset. The whole structure is otherworldly, a cosmic plume that dwarfs any planet, yet it emanates from a core no larger than a mountain. It is as if a snowball the size of a city has lit a long torch in the vacuum of space. You marvel at the contradiction, how something so small can create a vision so huge and splendid. But that is the nature of comets, those dirty snowballs of the solar system. They carry within them the potential, under the sun's touch, to become ephemeral giants, with tails millions of kilometers long that can stretch across the sky. As you watch, the comet slowly glides against the backdrop of stars. It moves noticeably from night to night, a visitor on its way through our cosmic neighborhood. This very movement, so slow and stately, hints at the comet's long journey. It came out of the dark, and it will return to the dark, following a grand elliptical path around the sun. Its appearance is a brief performance in the inner solar system, a visit to the realm of sunlight before it heads back to cold outer reaches. The thought tugs at something in your heart. You are seeing a traveler that has spent most of its life in darkness, far beyond the worlds we know, and soon it will be gone again. There is an almost melancholy beauty to it. This lonely voyager flaring into glory when near the sun, then vanishing for centuries or millennia. And where did it come from, this ancient wanderer? To truly appreciate the comet, one must trace its origin story out to the fringes of the sun's domain. It likely began its journey in the outermost regions of the solar system, a place where countless such icy bodies dwell. Some comets originate in a vast ring of debris just beyond Neptune known as the Kuiper Belt, the same region that harbors Pluto and other dwarf planets. Out there, in the frigid twilight at the edge of the sun's influence, lie innumerable frozen objects. For eons they orbit quietly, like embers left over from the solar system's formation. Every so often, a gravitational nudge, perhaps a slight tug from a passing planet, or the distant alignment of giants, disturbs one of these ice-laden worlds. It gets diverted from its stable path and sent sunward. What was once a remote, frozen chunk, invisible in the darkness, becomes a comet alive with light as it nears the sun. Other comets hail from even farther away, the mysterious Oort cloud, a spherical halo of icy bodies encasing our solar system at incomprehensible distances. The Oort cloud is thought to be a shell of trillions of cometary nuclei, stretching almost a quarter of the way to the nearest stars. Out there, the sun is merely a distant glimmer, and temperatures are only a few degrees above absolute zero. A comet born in the Oort cloud may spend millions of years circling in deep freeze, never coming near the inner planets. But occasionally, the subtle gravitational tides of the galaxy or the brief intrusion of a passing star jostles the Oort cloud. When that happens, one of these ancient icebergs can be dislodged, beginning a slow fall toward the sun. Such a comet arrives from any direction. Unlike Kuiper Belt comets, which travel near the plane of the solar system, an Oort cloud comet can plunge in from the north, south, or anywhere. Many of the great comets of history, those with extremely long periods, or even one-time visitors, began their journeys here, in the solar system's distant comet cradle. Our comet tonight might be one of these long-lost children of the sun, returning for a brief reunion, or perhaps a younger, shorter period comet from the Kuiper Belt, making more frequent trips. In either case, it carries a priceless cargo, the primitive material of the early solar system. These outer regions, whether the Kuiper Belt or Oort cloud, are cosmic deep freezes. They preserve the composition of the solar nebula, the cloud of gas and dust from which the sun and planets formed, nearly unchanged for billions of years. This comet's nucleus is a time capsule from that epoch of creation. Inside it are ices that condensed in the original protoplanetary disk before even Earth existed. Every molecule of water ice, every grain of dust within the nucleus, has a story to tell about the formation of the planets. If one could hold a piece of that nucleus in hand, with thick, insulated gloves of course, you would be holding something almost unchanged since the birth of the solar system. The comet's ice is a mix of water, yes, but also other exotic ices, carbon dioxide, dry ice, carbon monoxide, methane, ammonia, perhaps even more complex compounds like methanol or formaldehyde. These were the ingredients available in the outer regions of the Sun's natal disk. Embedded in the ice are particles of rock and dust, silicates and metals that once floated in the protoplanetary cloud alongside the ices. Many of those dust grains are minuscule time travelers themselves, tiny stardust grains that predate our Sun, forged in the envelopes of ancient stars and cast into the galaxy before being caught up in the cloud that formed our solar system. Others are fragments that formed near our infant Sun and were then flung outward to mix with cold ices, a testament to the turbulent mixing in our solar nursery. Each comet, then, is a miniature museum of solar system history, containing both the coldest ices and traces of the hottest fires from our system's birth. As the comet's nucleus races through space, its ices vaporizing and dust spewing out, it actively sheds this ancient material. The very dust you see glinting in the tail was once part of that primordial nebula, now catching sunlight once again. In a poetic sense, the comet is sharing its memories as it travels by. Its ice is memory, its dust is story. The ice carries the memory of the solar system's infancy, preserving chemical signatures of the era when planets were just coalescing. The dust carries the story, each mote a tale of high heat or interstellar journey, of collisions and condensations long ago. Together, released in the comet's luminous wake, they weave a narrative of creation for those who know how to read it. Scientists have indeed learned to read some of that narrative. Space missions have sampled comet dust, and within those tiny grains, they discovered complex organic molecules, the stuff of life's prelude. It turns out that comets are laden with carbon-based compounds, chains and rings that form easily in the chemistry of interstellar space and protoplanetary disks. When the Stardust probe brought dust from Comet Wild 2 back to Earth, laboratory analyses revealed glycine, a simple amino acid, and a variety of other organic molecules. Think of that, building blocks of life, found in the tail of a comet. And not just one or two. Comets seem to be rich in organics, with some scientists estimating that perhaps half of the dust by mass is composed of complex organic material. These are not living things, but they are the raw ingredients from which living chemistry can spring. In addition, analysis of comet samples and observations shows they often contain a lot of carbon, hydrogen, oxygen, and nitrogen, the very elements that make up our bodies. Phosphorus has been detected too, another element vital for life, present in DNA and cell membranes on Earth. In essence, comets carry a toolkit of life's essentials kept on ice. This realization has dramatically expanded our appreciation for what comets are, not just icy dirt balls, but potentially couriers of life's ingredients across the cosmos. They travel with stores of water, myriad organic molecules, and even simple amino acids, preserved in the deep cold and delivered to any world, lucky or unlucky, enough to cross their path. But these ingredients remain locked within until the comet nears the Sun. Only then does the great thaw begin. Right now, as you watch our comet in the sky, the very process that allows us to see it is also a kind of unveiling. Gas and dust from the nucleus are being released and illuminated, giving scientists a brief chance to study what the comet is made of. Telescopes are trained on its spectrum, decoding the chemical fingerprints. Water vapor, cyanide, carbon dioxide, ammonia, yes, all are there, mixing into the night. A comet like this often carries more than 20 or 30 different detectable gases, a cocktail of volatiles that reads like a chemist's notebook of creation. Some of those gases, like a whiff of hydrogen sulfide or ammonia, hint at the complex reactions that occurred in the comet's frozen interior over time, as cosmic rays and sunlight slowly altered the ices. And what of the nucleus itself, that hidden kernel of ice and dust? If we could see it now, we might be surprised. Rather than a pristine white snowball, comet nuclei are often as dark as coal. After countless orbits, or even during a single close pass. A comet's surface can become encrusted with a layer of dark, carbon-rich material, like a charred crust, left behind after more volatile ices sublimate away. This dust mantle dulls the comet's reflectivity, making the surface absorb most sunlight. Indeed, when spacecraft finally photographed comet nuclei up close, they appeared charcoal black, peppered with bright jets where geysers of sublimating ice burst through the crust. So our comet's brilliant display hides a secret. Its core is likely a somber, dark wanderer, illuminated only by the halo of its own making. Deep within that core, shielded perhaps by layers of dust, there may remain ices that have not been touched by warmth since the beginning. Those inner ices will keep the comet's ancient memory intact until perhaps another journey, another age. Thus, the comet stands revealed in our mind's eye, a relic of Genesis, a composite of fire and ice, memory and story. Ice as memory, dust as story. The comet brings both to us. As it travels closer to the sun, it sheds more of that material, as if slowly turning the pages of a very old book written in water and carbon. Each glimmer in its tail is a syllable from that book, telling of the time when the sun was young and the planets were only grains and clumps in a disk. And we, fortunate latecomers, get to witness this tale written in light across the sky. Now the comet is nearing its closest approach to the sun. With each passing hour, it grows a bit brighter and its tails stretch a bit longer, responding to the intensifying solar energy. This is the climax of its transformation, from a quiet, frozen body to a dynamic celestial phenomenon. Soon it will round the sun and begin its long voyage outward again. But what path does it follow exactly? How do these wanderers move through the solar system, and how long until this one might return? The next act in the comet's story is one of motion, an elegant dance on the strings of gravity with a tempo measured in centuries and millennia. The comet's journey is governed by celestial mechanics as precise as they are grand. This glowing visitor is not wandering aimlessly through the night. It is obeying the sun, bound in an extended ellipse by the star's gravity. Most comets travel on elongated orbits that carry them from the deep freeze of the outer solar system into the warm inner regions and back out again. Some ellipses are so stretched that they are nearly open paths. The comet spends only a fleeting few weeks or months near the sun and decades or centuries out in darkness. Our comet, too, is tracing such a path. Night after night, as you have observed, it shifts position among the stars, moving faster as it draws nearer to the sun's embrace. It is like a prodigal child rushing through the inner solar system, swinging around the sun, and then set to flee back to the outer darkness. Each comet's orbit has its own rhythm. Some, like the famed Halley's Comet, complete a circuit in roughly a human lifetime, appearing about once every 75 years or so, returning to our skies across the generations. Halley's Comet has been recorded since antiquity, each visit a bookmark in human history, connecting disparate eras with its periodic light. Many other comets have longer periods, hundreds, thousands, even millions of years, and some are on trajectories so expansive that they will never return at all. After one pass by the sun, they are flung on escape paths into interstellar space, never to be seen again. Our current comet might be a long-period one. Perhaps it last visited when humans had just begun building cities, or perhaps it has never been here before at all, making its inaugural swing into the inner solar system since the time it formed. As the comet loops around the sun at its closest approach, the moment called perihelion, it reaches its greatest velocity. The sun's gravity pulls it into a swift slingshot. Then, as it recedes outward, it gradually decelerates, like a runner tiring on a long uphill climb. If we could trace its path from high above, we'd see a graceful elongated ellipse or perhaps a near parabolic arc, with the sun offset from the center. The comet's motion is a kind of physical poetry, a dance governed by Kepler's laws of orbital motion, speeding up when near the sun, slowing far away, sweeping out equal areas in equal times. In its motion, we can almost sense the ticking of a cosmic clock. Indeed, motion is time for a comet. For Halley's Comet, one orbit is roughly a human lifetime. For others, one orbit might outlast human civilizations. The orbital period of a comet becomes a measure of time on a scale far grander than our own. It reminds us that what seems a brief spectacle to us may be just one heartbeat in the comet's own centuries-long year. Now imagine the fate of our comet after this swing by the sun. It will recede into darkness again, but not quite the same as it arrived. Every visit to the sun transforms a comet a little. The heat vaporizes some of its ice, carrying away a portion of its mass. Sometimes the very shape of the nucleus may change. Surfaces carved by jetting gas, cliffs collapsing as supportive ice beneath them dwindles, new fractures forming from thermal stress. A comet is not static. It's evolving with each passage. In a sense, these are living worlds in dormancy that awaken, shed material, and then return to slumber. Over many such cycles, a comet can drastically alter. Some comets, especially the ones on shorter orbits that pay frequent visits to the sun, so-called periodic comets, gradually run out of the volatile ices that make them spectacular. Their once active surface may become covered in thick insulating dust, and the dramatic outgassing wanes. They become shadowed relics, dark, inert objects that masquerade as asteroids. Astronomers suspect that several near-Earth asteroids are actually extinct comets, comets that have shed their icy mantles and are now quiet, rocky bodies orbiting the sun without coma or tail. It's an intriguing life cycle, born in the distant cold, briefly flamboyant in youth and middle age when the sun's heat makes them grow comas and tails, and eventually settling into old age as a dormant, coal-black husk. Yet some comets meet far more dramatic fates. Not all survive their trip around the sun intact. Occasionally, a comet ventures too close to the sun, and the intense tidal forces and heat rip it apart. One famous example was Comet Ison in 2013, which swooped extremely close to the sun, so close that the solar furnace boiled it to destruction. Observers hoped to see it emerge from behind the sun as a dazzling object, but it disintegrated, leaving only a fading ghost of dust. There are also comets known as sun grazers that routinely dive near the sun. Many of them perish similarly, evaporated in a single fatal solar kiss. Comets can also break apart far from the sun. Sometimes internal pressures from heating, or perhaps a rotation that becomes too rapid due to jets acting like thrusters, cause the nucleus to fracture. In the mid-19th century, astronomers watched Biela's comet split in two. By the next few passes, the fragments had further crumbled and the comet eventually vanished. But it wasn't entirely gone. Years later, Earth's sky was lit by an unexpected meteor storm, the Andromedids, as our planet swept through a stream of debris that was once Biela's comet. The cosmic snowball had become a cloud of shooting stars. It was a striking lesson that comets and meteor showers are intimately linked. The dust that a comet leaves in its wake continues to orbit along the comet's path, and if Earth's orbit intersects that path, we are treated to a meteor shower. Every August, when we enjoy the Perseid meteors, we are actually witnessing the dusty legacy of Comet Swift-Tuttle. Each swift streak across the sky is a particle from that comet burning up as it plows through our atmosphere. In October, the Orionids are the remnants of Halley's Comet. Thus, even as a comet travels onward or disintegrates, it leaves behind a story in the form of meteors, a cosmic memory that can recur annually, like the echo of the comet's visit. Fragmentation can sometimes turn one comet into a family. The pieces of a shattered comet may themselves continue as smaller comets, at least for a time, each fragment developing its own coma and tail, if it still has enough ice. In the early 1990s, Comet Shoemaker-Levy 9 was drawn too close to Jupiter and was torn into a chain of over 20 fragments by the planet's gravity. These fragments then, famously, plunged into Jupiter a year later, one after another, like a string of celestial firecrackers, in July 1994. Over several days, Each fragment slammed into the giant planet, leaving enormous dark scars in Jupiter's cloud tops, some larger than Earth. It was a stark reminder of how fragile these cosmic ice balls are, and how violent the solar system can be. Even when a comet remains intact, it is in a continual dance with the sun's influence through the solar wind. Earlier we touched on how the solar wind shapes the ion tail, but the sun's breath can do more than shape. It can at times dramatically resculpt the tail. The ion tail is made of charged particles, so it responds to the solar wind's magnetic field. When a particularly strong gust of solar wind, or a coronal mass ejection, an eruption of plasma from the sun, blasts a comet, it can cause a phenomenon breathtaking to behold. The comet's plasma tail can be severed. Observers have seen a comet's tail detach and drift away into space like a loose ribbon when struck by a solar storm, only for a new tail to begin growing from the coma afterward. It's as if the sun momentarily snatched the comet's flowing hair, and the comet calmly grew it back once the solar tempest passed. Such events underline that the comet is not a static beam of light, but a dynamic structure constantly responding to the environment of space. The solar wind, invisible to our eyes, plays puppeteer with the glowing tails, sometimes twisting them into knots or causing them to kink and ripple, other times snapping them off entirely and forcing the comet to regrow its luminous train. All these transformations, sublimation, fragmentation, disintegration, and interaction with the solar wind, form the life cycle of a comet. They are born quietly in the darkness, flare to glorious life as they approach the sun, and eventually, one way or another, they fade. But in doing so, they deposit material into the inner solar system, scattering dust and gas that can have effects far beyond their brief visitation. Think of how meteor showers enrich our skies, or how comet dust adds a trickle of material to Earth's atmosphere each year. On rare occasions, something far larger than dust might strike Earth, linking a comet's fate directly with our own. Indeed, to fully grasp the significance of comets, we must explore not just their physical life cycle, but their influence on the cycles of planets and possibly life itself. For the story of comets is intertwined with the story of Earth. Long before there were eyes to marvel at comets, when Earth was a molten young planet, comets may have been raining down upon it. And long after we are gone, a comet could be the harbinger of great change on this planet once again. Comets give, and comets take away. They are agents of chaos and creation in equal measure. To see how, we look back into the deep past of our own world. Eons ago, in the chaotic infancy of the solar system, Earth was a barren, searing world, pummeled by constant impacts. It was a realm so hot that any water present at its birth would have boiled off or been baked into the rocks. And yet today, Earth is a water world, its surface mostly ocean, and it teems with life built from complex organic molecules. How did our once dry planet gain its life-giving water and carbon chemistry? Comets are central characters in one prevailing theory. In those primordial days, countless comets and asteroids were flung inward by the gravitational jostling of the newly formed giant planets. This period, known as the Late Heavy Bombardment, was a time of intense rain, of cosmic debris falling through the skies. Amid the storm of meteoroids and asteroids, many comets likely plunged toward the sun, some crossing Earth's orbit along the way. These icy interlopers smashed into the young Earth, releasing torrents of water and myriad organic compounds upon the surface. Each comet impact would have been catastrophic locally, but collectively, over millions of years, they may have delivered a substantial portion of Earth's oceans. Picture comet after comet vaporizing on impact, their water contributing to an atmosphere thick with steam, which eventually cooled and fell as rain to fill basins and carve out oceans. Along with water came organics, simple carbon molecules, maybe even amino acids, that had formed in the comet's ices or on dust grains within them. These were scattered like seeds upon the sterile early Earth. It's a hypothesis that has gained support from scientific detective work. By comparing the isotopic flavor of water, specifically the ratio of heavy hydrogen, deuterium, to normal hydrogen in comets and Earth's oceans, researchers seek clues to our water's origin. Some comets have water that is a close match to Earth's ocean water, suggesting they could indeed be contributors. Others have water that is heavier or alien in composition, which initially cast doubt on comets' role, pointing more to asteroids as the main water bearers. But then a pattern emerged. Certain comets known as hyperactive comets, which spew out more water than their surface area suggests because they expose fresh ice in outbursts, have water with an isotopic signature similar to Earth's. One famous example is Comet 103P Hartley 2, whose water was found to be much like Earth's. The thinking is that these hyperactive comets dredge up water from deep inside their nuclei, water that was protected from fractionation, the loss of lighter hydrogen, and retains an Earth-like fingerprint. If so, perhaps many comets hide Earth-like water in their interiors, only releasing it under certain conditions. The debate isn't fully settled, but it's increasingly plausible that a meaningful fraction of our oceans is cometary water. Beyond water, the delivery of organics might be even more crucial. Earth's nascent environment had to gather the raw materials for life, and comets were like cosmic delivery trucks for complex carbon molecules. The discovery of amino acids in comet dust and of organic compounds like sugars and nucleobases in meteorites suggests that the basic toolkit for life's chemistry was readily available in space and likely rained down on the early Earth. It's a humbling thought. The carbon in your muscles, the nitrogen in your DNA, some of those atoms and molecules could have arrived in the fiery plunge of comets long ago. We are, in a very real sense, part comet. In those tumultuous early times, each fiery impact that delivered water also delivered destruction. But Earth eventually cooled, water pooled, and chemistry began to stir in those waters. Perhaps the organics from comets mixed with those from asteroids and from Earth's own atmosphere to form the soup of life's beginnings. Some scientists even speculate about comets not just seeding ingredients, but possibly ferrying actual microscopic life, though the survival of life through the trauma of space travel and impact seems very unlikely. More concretely, comets likely helped set the stage for life on Earth by providing the ingredients and maybe even triggering environments like impact-heated pools or hydrothermal systems, where those ingredients could assemble into self-replicating molecules. So the comets, which for so long were feared as omens of death, may have been in part bringers of life. It's a beautiful irony. The disastrous stars, as ancient people called them, from the Latin dis aster, bad star, possibly delivered the water we drink and the carbon frameworks on which our bodies are built. With each comet that we study, we learn more about this connection. The Rosetta mission's findings of complex organics and the presence of glycine in Comet 67P reinforce that comets carry many of life's building blocks. And just think, every meteor shower that sprinkles Earth is perhaps delivering a few more microscopic grains of exotic carbon or specks of prebiotic matter into our environment. The exchange between Earth and comets didn't end in the distant past. It continues at a slow drip even now. Looking up at our comet now, you might see it differently knowing this. It is no longer just a distant light. It is a relative of sorts, a visitor from the family that helped create our home's oceans and air. The emotional experience of seeing a comet, already intense, gains another layer: gratitude. Without such celestial wanderers, Earth might have remained a dry rock. There might have been no ocean voyages or clouds or rain, no life as we recognize it. The cosmos, by means of comets, may have nurtured the conditions for us to exist. Yet the relationship between comets and Earth is not solely nurturing. History shows it has also been occasionally catastrophic, and potentially could be again. The same impacts that brought water in the distant past could, in a later era, bring ruin. To understand that duality, consider not just the deep past, but events within human memory and scientific observation. Consider those famous comets that have intersected not with Earth directly, but with our understanding and fears. Let us recall some of the notable comets that have blazed into human history, shaping culture and science, and even one that collided with a planet in our own lifetime. They each have lessons to teach about both the promise and peril of these cosmic wanderers. Throughout the ages, a few comets have stood out so vividly that they earned a place in human memory and history. They became more than just celestial objects. They became characters in our cultural story. One such comet is Halley's Comet, arguably the most famous of all. It is a returning wanderer, revisiting the inner solar system roughly every human lifetime. This periodic nature, first confirmed by the astronomer Edmund Halley in the 18th century, means Halley's Comet has been observed again and again through recorded history. It has woven itself into the fabric of human events. In the 11th century, a bright comet, later identified as Halley, appeared over Europe. So astonished and fearful were people that they even embroidered it into the Bayeux tapestry, linking it to the Norman conquest of England. To them, it was a harbinger of great upheaval. A few centuries later, near the dawn of the 14th century, Halley's Comet graced the heavens again. The Italian artist Giotto di Bondone, inspired by its appearance, painted a comet as the Star of Bethlehem in one of his frescoes. This is a rare instance of a comet being portrayed as a positive omen, a divine sign of hope. Halley's Comet has often served as a convenient scapegoat for tragedy. Each time it returned, people searched their histories for disasters to blame on it. By the early 20th century, science had advanced, yet when Halley approached in 1910, public anxiety still ran high. Earth was due to pass through the comet's tail. Although astronomers knew the gases were too diffuse to harm us, sensational newspapers warned of poisons in the tail. Entrepreneurs sold comet pills and gas masks to a fearful public. When nothing dire occurred, humanity edged another step away from superstition. This same comet has also marked personal stories. Famed American writer Mark Twain was born under Halley's Comet on one of its visits, and he predicted he would go out with it on its return. Indeed, he died the day after it reappeared decades later. Halley's Comet, coming like clockwork roughly every 75 years, has become a symbol of continuity amid change. It has been recorded since at least 240 BC by Chinese astronomers. It was the comet of the Norman conquest, the comet of Twain, and it will be the comet of generations to come. When it returns in the mid-21st century, it will connect yet another chapter of human history to all those past. Each return of Halley's Comet has taken it further from an omen and closer to an old friend, one that maybe, just maybe, helped inspire us to learn the laws of celestial motion. After all, Edmund Halley's bold prediction of its return was vindicated when it duly arrived on schedule in the mid-18th century, a triumph of reason over fear. Another comet that left a deep impression is Comet Hale-Bopp, the great comet of 1997. Hale-Bopp was discovered 2 years before its closest approach, which gave the world plenty of time to anticipate its performance. And perform it did. As it neared perihelion in 1997, Hale-Bopp became one of the brightest comets of the 20th century. It was visible to the naked eye for a record 18 months, an almost unheard of duration. Night after night, people could step outside and see its brilliant form hanging in the sky. It sported a dazzling white dust tail and a delicate blue ion tail, both clearly visible even from light-polluted cities. Under dark rural skies, Hale-Bopp was breathtaking, a luminous apparition with twin tails fanning out, one a broad curved sweep of pale gold, the other a straight ray of electric blue. Many who saw it still speak of it as the once-in-a-lifetime spectacle it was. Hale-Bopp became a media sensation, drawing millions of casual observers out to look upward. For the vast majority, Hale-Bopp was a source of joy and wonder. Families had comet-gazing picnics. Photographers took stunning images that adorned magazine covers. It reminded humanity that even in the late 20th century, with entertainment on screens and lights drowning out the stars, a natural celestial event could captivate the world. Sadly, there was a darker footnote. A cult called Heaven's Gate believed a spaceship was following the comet and committed mass suicide as Hale-Bopp peaked. A tragic reminder that even in modern times, comets can inspire dangerous fantasies in the unhinged. But for nearly everyone else, the comet was purely a wonder, not a portent of doom. It also provided scientists a prolonged opportunity to study a bright, active comet. Its great intrinsic brightness, partly due to an unusually large nucleus, tens of kilometers wide, and long duration, allowed detailed observations of its behavior, providing a wealth of data on cometary gas and dust dynamics. After 1997, Hale-Bopp receded toward the outer solar system. It won't return for over 2,500 years, but it left an enduring memory that will be recounted in astronomy books and by those who saw it. In more recent times, comet Neowise, officially CE 2020 F3, became a household name. In July 2020, during a period of global isolation and anxiety, this unexpected visitor offered a celestial respite. Discovered by a space telescope only a few months prior, Neowise survived its passage by the Sun and emerged into the Northern Hemisphere's evening skies as a striking object. For those who ventured out at dusk or before dawn, often from backyards or lonely country roads, Neowise displayed a graceful golden dust tail and a fainter ion tail. It wasn't as brilliant as Hale-Bopp had been, but it was the most impressive comet in decades, easily visible to the naked eye, especially under clear, dark skies. Photographs of Comet Neowise went viral. Images of a curving comet above city skylines, above quiet, pandemic-deserted streets, above mountain ranges and lakes. People across the Northern Hemisphere, many seeing a bright comet for the first time, found solace and even delight in its presence. For a few weeks, news feeds and social media were filled not just with earthly troubles, but with photos and exclamations about the comet. It felt like a gift from the universe in a troubled year, a reminder that beyond our immediate crises, there is still beauty and wonder. Neowise 2 is now departing on a long orbit, not to return for nearly 7 millennia. Its visit was fleeting but uplifting, a kind of cosmic encouragement at a time when humanity needed a bit of hope and perspective. Not all notable comets are remembered for gracing Earth's skies. Some are famous for their fate elsewhere. Comet Shoemaker-Levy 9 is one such comet, known not for a spectacle to human eyes, but for a dramatic cosmic collision. In 1993, astronomers Carolyn and Eugene Shoemaker and David Levy discovered a strange, squashed-looking comet near Jupiter. It turned out that this comet had been captured by Jupiter's gravity and torn into pieces. By 1994, those pieces, over 20 of them, were on a collision course with Jupiter. In July 1994, the world watched as, one after another, the chain of comet fragments slammed into Jupiter's southern hemisphere. Each impact released energy equivalent to many millions of nuclear bombs. Earth-based telescopes saw huge dark blotches appear on Jupiter's clouds, bruises the size of Earth itself, where plume after plume of debris rose and fell. This was the first time in history that humans directly witnessed a collision between two celestial bodies. The event riveted astronomers and the public alike. It was sobering. If such a fragment, a few kilometers across, had hit Earth, we would be looking at an extinction-level event. Thankfully, mighty Jupiter took the hit. In fact, Shoemaker-Levy 9's demise underscored Jupiter's role as a cosmic guardian. Its gravity often sweeps up comets that might otherwise menace the inner solar system. The comet's dramatic end gave planetary scientists an unprecedented look at an impact's effects and, in a sense, served as a wake-up call about cosmic impacts in our own neighborhood. It taught us that giant impacts are not just relics of the distant past. They can happen in real time, in our cosmic backyard. These 4 comets, Halley, Hale-Bopp, Neowise, Shoemaker, Levy 9, each tell a different tale. Halley connects us to history and the cyclical nature of time in the heavens. Hale-Bopp dazzled with its brilliance and longevity, uniting people in collective awe. Neowise arrived as a serendipitous gift during a dark time, a reminder of wonder beyond our immediate troubles. Shoemaker Levy 9 dramatically illustrated the ongoing power of cosmic events and our need to pay attention to the skies not just for inspiration, but for safety. Through them, we see the many faces of comets, periodic and familiar, sudden and spectacular, gently inspirational, or violently instructive. They have been interpreted through the ages as omens or miracles, and now we interpret them as natural phenomena rich with information. In understanding these comets, we better understand the solar system and ourselves. For much of human history, comets were enigmatic, often feared. The sudden appearance of a comet, unpredictable and striking, shattered the normalcy of the night sky. To people who believed the heavens reflected divine will or signaled events on Earth, a comet's arrival was an intense portent. Ancient Chinese records called comets broom stars or guest stars and linked them to the rise and fall of emperors. In Europe, comets were long viewed as the terror of kings. When a bright comet appeared, it was said to foretell the death of a ruler or a great disaster. The very word disaster comes from Latin roots meaning bad star, showing how deeply that fear was ingrained. Yet, as our understanding grew, the mythological gravity of comets began to fade, replaced by scientific gravity, Newton's gravity. In the late 16th century, the Danish astronomer Tycho Brahe observed a bright comet and noted that it showed no measurable parallax against the background stars. This meant the comet was farther than the moon, contradicting Aristotle's long-held idea that comets were mere atmospheric phenomena. Tycho's revelation placed comets in the celestial realm of planets and stars, subject to the same physical laws. Then Edmund Halley's prediction and the comet's return cemented the idea that comets follow regular orbits, not the caprice of gods. What used to inspire mass panic gradually came to inspire mass curiosity instead. Today, instead of fearing comets, we send spacecraft to meet them face to face. We seek to know them intimately. This transition from dread to curiosity is one of the triumphs of human intellect. But even now, knowing what they are, comets have lost none of their capacity to astonish. A great comet in the sky can still make even a jaded city dweller stop in their tracks and feel small and in awe. Perhaps we no longer see a fiery sword of the gods, but we do see a marvel of nature, and that is more than enough to stir the soul. In our modern quest to understand, we have embarked on a new chapter, sending robotic emissaries to chase comets down and unravel their secrets. The era of modern missions has brought comets within our reach and understanding like never before. In the mid-1980s, as Halley's Comet approached once more, humanity seized the opportunity to greet it with technology. In 1985, the European Space Agency launched Giotto, a spacecraft designed to fly by Halley's Comet during its 1986 visit. Giotto was a small, hardy probe equipped with cameras and instruments to sample the dust and gas around Halley's nucleus. No one knew exactly what would happen as it zoomed through the comet's coma. The risk to the spacecraft was high, like flying through a blizzard of grit at tens of kilometers per second. On the night of closest approach, in March 1986, Giotto hurtled past Halley's nucleus at about 600 kilometers distance. It was pummeled by dust. A grain even knocked its camera off alignment for a moment. But Giotto survived and sent back the first ever close-up images of a comet's heart. Those images were historic and mesmerizing. They revealed a dark, potato-shaped nucleus about 15 kilometers long, jetting brilliant streams of material into space from a few active regions. Only a small portion of Halley's black, carbon-crusted surface was actively venting gas. The rest remained dormant and oddly dark, reflecting only a few % of sunlight. Halley's Comet was not a translucent ghost, but a solid world, a very dark one, among the blackest objects in the solar system, wrapped in its self-made haze. Giotto's instruments also confirmed the richness of Halley's chemistry, detecting water vapor, carbon monoxide, methane, ammonia, and complex organic molecules. This encounter was humanity's first intimate meeting with a comet, and it transformed our picture of them. They were not fluffy, airy bodies, but solid, complex mini-worlds with varied terrain and ingredients. After Giotto's pioneering flyby, a bold idea took shape. Why not bring a piece of a comet back to Earth? That idea became reality with Stardust, a NASA mission launched in 1999. Stardust's target was Comet Wild 2, and its goal was audacious: fly through the comet's coma, catch particles streaming off the nucleus, and return them to Earth for detailed study. In January 2004, Stardust swooped within 240 kilometers of Wild 2's nucleus, exposing a tennis racket-shaped collector filled with aerogel, a lightweight, frothy material, to snare dust particles without vaporizing them. It also snapped pictures of Wild 2's nucleus, revealing a surface riddled with deep pits and spires, looking like a battered ice rock world with many vents. The flyby was harrowing. The spacecraft was hit by a spray of particles that caused it to wobble, but it stayed on course. In 2006, Stardust's sample capsule parachuted to a safe landing in the Utah desert. Inside was precious cargo, thousands of tiny comet dust grains, the first samples from beyond the moon ever returned to Earth. When scientists analyzed Stardust's catch, the results were thrilling. They found minerals that form at high temperatures, like olivine and other crystalline silicates, mixed among the expected ices and carbon compounds. This suggested that material from the inner solar system had somehow traveled outward to mix into comets forming at the fringe. They also definitively found glycine, a simple amino acid, in the samples, proving that such biologically relevant molecules form in comets and can survive eons in space. The comet dust had a large component of complex hydrocarbons as well, a sort of cosmic tar. The Stardust mission showed directly in the lab that comets harbor the raw ingredients that would have been useful to the origin of life on Earth. For the first time, humanity held in its hands pieces of a comet, pieces that smelled of ammonia and almonds, as scientists described the scent of the sample upon opening the canister, owing to trace organics. We were touching the very stuff that had probably helped seed our planet. While Stardust was still en route back to Earth, another daring mission was underway: Deep Impact. This 2005 NASA mission had the dramatic goal of punching a hole in a comet. The target was Comet Tempel 1. Deep Impact carried a 370-kilogram copper impactor, which it released directly into Tempel 1's path, while the main craft observed from a safe distance. On July 4, 2005, the impactor smashed into the comet's nucleus at over 10 km, excavating a crater and throwing up a huge plume of dust and gas. Telescopes on Earth and Deep Impact's mothership watched the flash and debris. The impact ejected subsurface material that hadn't been exposed to sunlight. Analysis of the ejector showed a lot of fine powdery dust, more than expected, and revealed the presence of carbonates and clays, minerals that form in liquid water within the comet. This was a surprise. Perhaps Tempel 1 had mild internal heating or water at some point to produce such minerals. The comet seemed to have a very fluffy, porous interior, so much so that the crater it created was larger and gentler, walls that collapsed inward, than anticipated. Deep Impact effectively did a controlled excavation of a comet and found that beneath a relatively solid crust was softer, perhaps more fragile material. It was our first comet geology experiment. Later, in 2011, another mission, Stardust Next, flew by Tempel 1 and imaged the Deep Impact crater, confirming it was about 150 meters across. Through Deep Impact, we learned not just composition, but also something about the structural strength and layering of a comet. It was like knocking on a door and hearing an unexpectedly hollow sound from within. If Giotto opened the door and Stardust and Deep Impact peered through, Rosetta moved in and stayed for a while. The European Space Agency's Rosetta mission, launched 2004, was breathtakingly ambitious: to rendezvous with a comet and accompany it for over 2 years, observing it up close as it approached the Sun and even landing a probe on its surface. After a 10-year journey, Rosetta arrived at Comet 67P Churyumov-Gerasimenko in mid-2014. The images it sent back of Comet 67P were astonishing. The nucleus was shaped like a rubber duck, 2 lobes connected by a narrow neck. This bilobed shape hinted that 67P might be the result of a gentle merger of 2 separate comets in the past. Rosetta entered orbit around 67P, mapping its surface in unprecedented detail. It revealed towering cliffs, pit-like depressions venting jets of vapor, fields of boulders, and smooth plains of dust drifts. This was not a simple, dirty snowball. It was a diverse little world with geological features and seasonal changes. In November 2014, Rosetta deployed its small lander, Philae, to attempt the first landing on a comet. Philae's harpoons failed to fire upon touching down, causing it to bounce twice. It finally came to rest in the shadow of a cliff. Though it didn't land perfectly, Philae still managed to conduct experiments during its initial battery life of about 60 hours. It drilled the surface, finding it surprisingly resistant beneath a softer crust, tasted the local vapors, detecting a bouquet of organic molecules, including some complex ones like nucleobase building blocks, and sent back panoramas from the comet's surface, an alien landscape of dark rocks and looming cliffs, lit by an eerie, faint sunlight. Philae's unexpected resting place meant its solar panels got little light, and it fell silent after a few days. But in those hours, it became the first human-made object to operate on a comet's surface, a truly historic achievement. Meanwhile, Rosetta continued orbiting and observing 67P from above. Over the next 2 years, it watched the comet come alive as it neared perihelion in August 2015. The frozen ground warmed and gushed out jets of gas carrying dust. Rosetta flew through these jets, measuring their composition. It sniffed a rich array of chemicals: water, carbon dioxide, carbon monoxide, methane, methanol, ammonia, hydrogen cyanide, formaldehyde, hydrogen sulfide. Hence the comet smelled of rotten eggs and urine, as scientists cheekily noted, and even molecules like glycine, the same amino acid Stardust found, and phosphorus. It was a chemical treasure trove. One of the biggest surprises was the detection of significant amounts of molecular oxygen, O2, in the comet's halo. This was completely unexpected because O2 is highly reactive and was not thought to survive from the solar nebula. Its presence suggested that 67P's clathrate ices might have trapped oxygen during the comet's formation, or that some other process was generating it. This finding alone kept comet scientists busy with new theories. Rosetta mapped the comet's gravity and found the nucleus had a density much lower than water ice. It was roughly 50–60% empty space. This confirmed the extremely fluffy, porous nature of comet interiors. It also observed changes on the comet. Portions of cliffs collapsed, new jets opened up, boulders moved, likely from gas outbursts. We were witnessing geology on a comet, slow by human terms, but fast by geological terms, happening in real time. As the comet passed its closest approach to the Sun and headed out, activity subsided. Rosetta continued to follow it until, in September 2016, with its mission ending, Rosetta was gently guided to impact on the comet's surface, taking close-up images down to the final moments. It came to rest on the comet, effectively becoming one with it. Through Giotto, Stardust, Deep Impact, Rosetta, and other missions, like a brief flyby of Comet Borrelly by Deep Space One in 2001, or of Comet Hartley 2 by Epoxy in 2010, We have transformed comets from distant, fuzzy apparitions into tangible worlds that we can visit and even sample. We found that comet surfaces can be as hard as rock in places and as soft as powder in others. We found organic chemicals of complexity beyond what many imagined. We confirmed that much of Earth's water could indeed have come from these ancient ice bearers. We learned that comets are diverse. Some might be built of two fused halves like 67P, others more single-bodied. Some are very chemically rich, others somewhat depleted, as Halley's Comet turned out to have an unusual composition with lots of organics and a relative dearth of water. We've learned that their behavior is not random, but driven by solar heating. Yet each comet has its own personality, with different regions turning on at different times, often dependent on the shape and tilt of the comet. Yet despite all these advances, mysteries still cloak comets. In fact, each discovery seems to open new questions. Among the biggest is how exactly comets formed. We know they coalesced in the outer solar nebula. But was it a gentle coming together of icy grains sticking bit by bit, or a more abrupt collapse of a clump of material? Evidence from Rosetta's images of 67P's goosebumps, small meter-sized clumps on the surface, suggests comets might be aggregates of smaller building blocks, loose piles of pebbles that assembled under weak gravity. Their high porosity supports this idea of a gentle assembly, like a cosmic snowdrift. But we haven't witnessed it directly. It remains an active area of research, with some leaning towards the pebble accretion model, and others considering whether large instabilities in the protoplanetary disk caused kilometer-sized comets to condense rapidly. We also still wonder what lies beneath the surface of comets. Rosetta gave us hints. 67P had a very homogeneous interior in density and likely no large voids, but we don't know if comets have internal stratification, like layers from different eras of accretion, or if they are rubble piles through and through. We haven't yet drilled deeply into a comet. Filey tried a shallow drill. Are comets perhaps clumps of material loosely held, or do they have cores of different composition? The Deep Impact experiment gave a peek, suggesting softer interior under a crust, but one data point isn't enough. The chemistry of comets also holds puzzles. That oxygen on 67P is one. Another is why some comets have much more carbon monoxide than others. Comet Borisov, the interstellar visitor we'll discuss soon, had an unusually high CO content. Does that reflect its birthplace around a different kind of star, or did it form in an extremely cold part of its original system? Even within our solar system, comets show compositional variety. For instance, comets from the Oort cloud versus Jupiter family comets from the Kuiper belt display different ranges of water isotope ratios. We're not sure if that's due to where they formed or how often they've been heated by the sun. Then there's the conundrum of activity outbursts. Comet Holmes famously brightened by a factor of 1,000,000 in 2007, temporarily becoming visible to the naked eye as a new star in Perseus. This happened when it was far from the sun. What caused that eruption? Possibly an internal pocket of volatile ices suddenly venting, or a major fracture exposing fresh material. We still lack a predictive theory for such outbursts. And fragmentations. Why do some comets, like Comet Atlas in 2020, just fall apart spontaneously even before reaching perihelion? Were they rubble piles loosely held that spun up too fast? Or did heat create cracks that rapidly propagated? Each fragmentation event we catch, and we caught many smaller ones with Rosetta on 67P, teaches us a bit more, but it remains somewhat unpredictable. The line between asteroids and comets has blurred too. We've found bodies in the asteroid belt, at much warmer, closer orbits, that show comet-like activity, the so-called main belt comets, or active asteroids. These likely have reservoirs of ice that occasionally get exposed. Are they comets that migrated inward and became dormant until hit by something? Or asteroids that somehow held onto pockets of ice for billions of years? It's a mystery that challenges the neat comet-asteroid divide. Perhaps in the end, comet is a behavior, outgassing, more than a strict category. and some asteroids can behave like comets if given the chance. Just as we began to settle into our new understanding of comets, the cosmos threw us a curveball from beyond our solar system. In recent years, a thrilling new chapter in the story of comets began with the appearance of objects from other star systems. These interstellar visitors have expanded our perspective and raised intriguing questions. The first of these was spotted in late 2017, an object later named Oumuamua, Hawaiian for Scout. It was the first confirmed interstellar object passing through our solar system. But Oumuamua did not announce itself with a coma or tail. It appeared as a dot of light, like an asteroid. As astronomers tracked it, they realized it had come on a one-way hyperbolic trajectory from far beyond and was already outbound. Oddly, it showed no signs of outgassing. No fuzzy coma was detected despite sensitive searches. Yet, as more data came in, something strange appeared. Oumuamua's trajectory was deviating slightly from what pure gravity would dictate. It was as if a gentle force were pushing it, akin to cometary outgassing. If it was outgassing, it must have been doing so in a way we couldn't easily see, perhaps releasing molecules like hydrogen that don't produce visible glow, or perhaps only very small amounts. And then there was its shape, inferred from its changing brightness. It seemed to tumble end over end, with its brightness varying by a factor of 10. To cause such variations, Oumuamua must be very elongated or very flattened. Some models suggested it might be cigar-shaped, perhaps 400 meters long and only 40 meters wide. Others suggested a thin pancake shape. Either way, it was unlike any comet or asteroid we had seen. Some scientists humorously pondered if it was an alien probe, a notion largely dismissed by data, but a sign of how perplexing this object was. The leading natural explanations were that Oumuamua was a fragment of a larger body tidally shredded by a star, or that it was a dry comet, one whose volatiles had been mostly spent, leaving it with just enough gas to nudge it, but not enough to form a visible coma. Another hypothesis was that it was made of exotic ices, like solid hydrogen, that could sublime without leaving a detectable signature. To this day, Oumuamua remains an enigma, a visitor that came and went before we knew what to make of it. Then, in late 2019, a second interstellar traveler appeared, and this one was unmistakably a comet. Discovered by amateur astronomer Gennady Borisov, Comet 2I Borisov arrived with a visible coma and tail. This was essentially an interstellar comet presenting itself exactly as our homegrown comets do. Borisov was observed for months as it swept through the inner solar system. Spectra revealed it contained water vapor, cyanide, diatomic carbon, all typical comet gases. Photographs showed a pretty ion tail. If we hadn't known its trajectory, Borisov could easily be mistaken for an ordinary long-period comet. Yet this was material from another star's nursery visiting us. One noteworthy finding was that Comet Borisov had an unusually high ratio of carbon monoxide to water in its vapor, far higher than most solar system comets. This suggested it might have formed in a colder environment. Carbon monoxide ice is very volatile and usually abundant only in very cold comets. Perhaps Borisov originated around a red dwarf star, or in the outer reaches of a system colder than ours. Apart from that, it was reassuringly familiar, which in itself was profound. It means the processes that form comets around other stars produce broadly similar outcomes. The juxtaposition of Oumuamua and Borisov was fascinating. The first was interstellar and weird, perhaps a piece of a comet's rocky core or something completely unexpected. The second was interstellar and yet comfortingly recognizable as a comet. These two barely begin to hint at the diversity of objects wandering between the stars. Our solar system likely ejected trillions of small objects during its formation too. Some of those might have reached other stars. Likewise, some comets in our Oort cloud might be immigrants from other stars born in the Sun's birth cluster. Interstellar comets are messengers between planetary systems. The realization that interstellar objects pass through and that we can detect them has energized scientists. Plans are being drafted for future missions that could try to intercept an interstellar object if one is discovered on approach. It's challenging. These visitors move fast on unpredictable paths, but not impossible with enough advance notice and a fast rocket or even a solar sail. One day, we might directly sample a comet from another star, analyzing alien ices in our labs. What an extension of our senses that would be. From all this, one clear lesson emerges. Comets, whether local or interstellar, connect us with the broader universe. They carry clues of cosmic history and even hints of cosmic commonalities. They show that the ingredients and processes that shaped our solar system are not unique. They likely happen in countless systems. Comets have been agents of creation, possibly delivering life's ingredients, but as history and shoemaker Levy 9 remind us, they can also be agents of destruction. It is natural then to contemplate comets and extinction events. Could a comet end life on Earth or drastically alter our world? The idea has moved from folklore, blazing star means end of the world, to serious science. About 66 million years ago, a catastrophic impact triggered a mass extinction that ended the age of dinosaurs. A huge crater off Mexico marks that event. For a long time, it was assumed to be an asteroid impact, due to certain mineral evidence in the debris layer. But some researchers have suggested it might have been a comet, specifically a fragment of a long-period comet flung in by Jupiter or the Sun's tidal forces. This hypothesis, while not mainstream, reminds us that comets can hit planets. If the Chicxulub impactor was indeed a comet, or a piece of one, then comets have literally reshaped the history of life on Earth. Even if it wasn't, comets surely have struck Earth over geological time, perhaps during epochs where the evidence has been eroded away or masked by other processes. Some scientists in the 1980s noticed a possible periodicity in mass extinctions and speculated that maybe every 26 million years, a shower of comets bombards the inner solar system, causing devastation. They even hypothesized a companion star named Nemesis, far out, whose orbit every 26 million years would disturb the Oort cloud. Nemesis has never been found, and the extinction periodicity is debated, but the notion of comet showers remains plausible. The Sun does bob up and down in the galactic plane, and encounters with passing stars happen from time to time. It's very conceivable that once every few tens of millions of years, the Oort cloud gets a gravitational kick, and a rain of long-period comets is sent inward. Most would miss Earth, but some might not, and even one large one could spell disaster. Thus, comets might be woven into the fabric of Earth's long-term biospheric ups and downs. On human timescales, fortunately, civilization-ending comet impacts are extremely rare, but smaller events remind us of the hazard. In June 1908, an object, likely a small comet or asteroid, perhaps 50 meters across, exploded above the Tunguska region of Siberia, flattening an immense area of forest. No crater was left. The body disintegrated in the air, which is one reason some speculated it was a comet. All ice and dust, no solid remnants. Whether comet or asteroid, the Tunguska event released energy comparable to a large nuclear bomb. Had it occurred over a city, it would have obliterated it. We now have observatories constantly scanning for near-Earth objects. We've catalogued thousands of asteroids that could come close, but a long-period comet could still surprise us. Typically, we might discover such a comet only months to a few years before it enters the inner solar system. That's not a lot of time to prepare if one were on a collision course. Thankfully, these long-period comets are far less common in the inner solar system than asteroids. But the uncertainty is higher. We can predict asteroid orbits decades ahead. A comet arriving fresh from the Oort cloud is an unwelcome wildcard, though one with low probability. We've already been developing defenses. In 2022, NASA's DART mission successfully tested nudging an asteroid's orbit by crashing a spacecraft into it. A similar method could work on a small comet if we had enough warning. Though comets often travel faster, and could be harder to hit precisely. Other ideas for a comet threat might include attempting to break it up, though that could make multiple dangerous pieces, or even using a standoff nuclear blast to vaporize or deflect it. These are measures of last resort. The preferred approach is early detection. See it coming far away, and then any needed deflection can be very small. This is where continued observation is key. The Vera Rubin Observatory, expected to begin full surveys soon, will scan the sky deeply and frequently, which should significantly improve our chances of spotting that proverbial comet on a collision course decades in advance, if one exists. Jupiter also stands as a protector. Its gravity slings many inbound comets out of harm's way, or even gobbles them up, as with Shoemaker-Levy 9. Still, we do not forget that what crashed into Jupiter in 1994 could just as easily have been aimed at Earth had the celestial dice rolled differently. Thus, comets sit at a profound junction of themes. They are bringers of both life and death. They connect the deep past with the present and future. They remind us of the fragility and also the resilience of life. After all, if comets did help start life on Earth, one could say we owe our existence to them. And if one day a comet threatens to extinguish life, it may be that life, in the form of human technology and ingenuity, will thwart it. There is a grand poetic symmetry to that. Mindful of both the promise and threat of comets, we look to the future and consider what lies ahead in our relationship with these celestial nomads. Each new comet mission has answered questions and raised others, and there are many plans brewing for further exploration. One eagerly anticipated project is ESA's Comet Interceptor, planned for launch later this decade. This innovative mission will not target a specific known comet. Instead, it will wait in space, at Earth's Lagrange point L2, until a suitable new comet is discovered inbound, ideally a pristine, first-time visitor from the Oort cloud. Once such a target is found, Comet Interceptor will redeploy to meet it. The mission actually consists of 3 spacecraft, a main probe and 2 sub-probes. As they approach the comet, the sub-probes will detach and fly by the comet at different distances and angles, while the main craft passes more distantly. This will provide multi-point measurements of the comet's gas, dust, plasma environment, and close-up views of its nucleus from different sides simultaneously. If all goes well, we might get our first look at a truly untouched comet, one that has never been fried by the sun before. Comparing its composition to comets like Halley or 67P, which have been cooked on repeated orbits, will help reveal what changes solar heating causes and what the original nebula material was like. Another tantalizing ambition is a comet sample return mission that brings back icy material, not just dust. Stardust brought dust and some very small volatile traces. But imagine returning to Earth with chunks of actual comet ice, kept frozen the whole way. Scientists could peer into that ice with microscopes, dissolve it and run it through analyzers, sniff its vapors in ultra-sensitive instruments. A direct interrogation of primordial material. One mission concept, called Caesar, has aimed to do just this with Comet 67P, and although not yet approved, the desire remains. There are formidable technical challenges, keeping a sample at cryogenic temperatures on the journey home, for instance. But the reward would be unparalleled. We could, for example, directly measure the ratios of noble gases in comet ice, which tell us about conditions of formation, or discover complex organics that don't survive being fragmented and heated in space. We might even find interstellar grains in the ice, tiny pre-solar minerals preserved within, that could be extracted and studied grain by grain. Even without returning samples, we have powerful new observatories to study comets from here. The James Webb Space Telescope, with its keen infrared vision, has already observed comets, detecting water and carbon dioxide, and even confirming the presence of water vapor around a main belt asteroid that turned out to be quietly comet-like. Webb can detect extremely faint outgassing at great distances, potentially catching comets beginning to awaken far from the Sun. Meanwhile, the Vera Rubin Observatory will, once operational, systematically scan the entire visible sky every few nights at unprecedented depth. This means it will catch new comets, likely in the outer solar system, and track changes in brightness or even detect splitting events. Rubin might give us early alerts for comets that could become great spectacles or, as discussed, any that pose hazards. Future missions are also considering touch-and-go landings, hoppers or rovers on comet surfaces. Philae gave a taste, but imagine a rover that could drive, or more likely hop in the low gravity, across a comet, studying variations, or drills that could go meters deep to bring up a core sample, like we do on Earth for ice records. Another idea is a cryogenic laboratory in space. Essentially, if returning to Earth with ice is too hard, one could have a spacecraft land on a comet, ingest some ice and dust, and perform detailed chemical analyses on site, transmitting the results. This would bypass the sample preservation issue, but let us examine volatiles in situ. And looking further ahead, one can dream of more novel interactions. Comets could even become resources for spacefaring humanity. They are rich in water and carbon compounds, the very materials needed for life support and fuel. Some futurists imagine capturing a small comet and nudging it into orbit around, say, Mars, to provide a water source for a colony. That's far-fetched with foreseeable technology, but not beyond the realm of long-term possibility. At the very least, learning how to extract water from a comet, perhaps by drilling a well and letting the sun's heat pump the water out as vapor, could be incredibly useful for future explorers. There's also something profoundly poetic in the idea of riding along with a comet. Some have suggested a comet hopper mission, a spacecraft that would essentially hitch a ride on a comet for an entire orbit, perhaps powering down during the frigid aphelion far out, then awakening as the comet comes sunward and directly witnessing the changes from the surface. Imagine a robotic observer clinging to a comet through the dark freeze of the outer solar system, and then holding on tight as jets erupt around it near the sun. It would be risky, but what an adventure. Essentially accompanying a comet on its journey as a human proxy. Our toolset for dealing with the threat side of comets will also improve. The more we learn about comet composition and structure, the better we can plan deflection missions. If we know a comet is mostly a loose rubble pile, a deflection might need a gentle nudge to push it whole, rather than something that might shatter it. If it has a sturdy core, maybe a harder shove is viable. The observations from DART's impact on an asteroid and Deep Impact on Temple 1 form early experiments in what might become a mature technology of planetary defense. It is comforting to know that whereas our ancestors could only cower from the wrath of the comet, we are moving toward being able to guard against it. As our missions grow bolder, so too does our philosophical perspective. We started by chasing comets for science. In doing so, we ended up chasing some very old questions as well. Where did we come from? Are we alone? Comets are involved in both. They carry clues of our origin and also distribute the seeds of life potentially between worlds. There's a hypothesis called lithopanspermia, that life can travel on rocks knocked off planets. Comets could facilitate that by transferring water and organics, or even capturing microbes in a glancing blow and carrying them elsewhere, though surviving the ejection and re-entry is an extreme long shot. Even if that never happened, the exchange of organics certainly did. Earth's early surface was likely enriched by cometary infall. The more we study comets, the more we realize they are threads in the grand tapestry of the solar system, threads that weave through the fabric of time and space, tying planets to the sun to the galaxy, the present to the deep past and future. They are not mere background actors, but have played pivotal roles in the story of Earth and possibly many Earths. Having journeyed with comets from deep time to the present and gazed toward their future, we find ourselves drawn into a reflective pause. What do these ancient wanderers truly mean to us, as thinking beings in the cosmos? It's time for a more philosophical reflection on comets, to ponder not just what they are, but what they symbolize and inspire. We have followed comets with our science and with our imagination. In doing so, we have perhaps come to know them better than our forebears did, yet they still evoke the same awe they always have. There is a sense that in understanding comets, we are understanding a part of ourselves as well, our origins and our place in the cosmos. Comets, in a profound sense, are time travelers. They carry memories of the solar system's birth. When we say poetically that a comet's ice is memory, we acknowledge that within each comet's frozen heart lies the unedited record of a time before Earth existed. It is as though the comet is a mindful ancient being, holding in its core the knowledge of where we come from. As it sublimates, that memory is released in the form of gas and dust, which we capture with instruments and translate into stories of creation. Thus, the dust is story. Each mote of dust from a comet is a chapter from the solar system's youth, whether it be a tale of a distant star that forged a grain of sand, or a tale of two planetesimals that gently merged. The comet's tail unfurls these tales across the sky, and we, with science as our language, strive to read them. Beyond the literal information they carry, comets stir something emotional and almost spiritual in us. The light is longing. The soft, otherworldly glow of a comet seems to reach across the vastness, stirring a sense of connection and yearning. Standing under a comet's glow, one can feel a tug at the heart, a longing for understanding and transcendence. Perhaps it is we who project that longing onto the comet, but it feels as if the comet itself is a cosmic messenger, reminding us of the broader universe, beckoning us to come and explore. That glowing tail is like an arrow pointing away from our small world, out to the great wide cosmos, awakening our desire to venture outward, or at least to send our thoughts far beyond the horizon. There is also deep symbolism in a comet's transience. A comet appears, captivates the world, and then fades away into darkness once more. It is a fleeting phenomenon, here for a few weeks or months, then gone for centuries or forever. This impermanence is a poignant mirror to our own mortal existence. We too blaze bright for a brief moment in cosmic time and then are gone. Yet, like comets, perhaps we leave something of ourselves behind, a meteor shower of influence, a memory in others, just as comets leave trails of meteoric dust that continue to intersect Earth's orbit long after the comet has departed. In that way, comets can symbolize the legacy we leave. They also teach us to appreciate the here and now. Every appearance of a great comet is unique and precious, something to be seized. How many people through history lived their whole lives without seeing a brilliant comet? To see one is a privilege. Comets thus remind us of the importance of witnessing and appreciating rare wonders when they occur. Comets also have a way of humbling us while simultaneously elevating us. When a bright comet dominates the night, we are reminded how small Earth is and how minor our daily concerns are against the backdrop of the cosmos. This is humbling. Many who have watched a comet felt that we are tiny under the stars feeling. At the same time, think of what it means that we, tiny as we are, can comprehend what a comet is. Through intellect and ingenuity, we have plucked the mystery out of that streak of light and identified it as a visitor from the fringes of the sun's domain, perhaps carrying ingredients that built our very bodies. Knowing that elevates us. We are not cowering creatures making up fearful myths. We are active participants in the cosmic story, understanding and even embracing these celestial phenomena. It's often said that we are stardust, and comets drive that truth home. The water in our bodies, the carbon in our cells, some of that is literally from comets or the same primordial cloud that birthed comets. We are linked by chemistry to these objects, and by studying comets, we are, in a way, studying ourselves and our origin. There's a profound unity in that realization. Comets, humans, planets, nebulae. We are all made of the same atoms, all part of the same grand cycle of matter and energy. Comets dramatize that cycle, formed from the solar nebula, possibly contributing to planets, maybe ending as meteor showers falling back to a planet, a full circle. Comets also ignite imagination like few other natural phenomena. They have always done so. They appear as if by magic, change visibly from night to night, and vanish into memory. They provoke questions about the unknown. Even today, a child seeing a comet for the first time might feel the spark of curiosity that leads them to become a scientist, an artist, a storyteller. In that sense, comets are muse and mentor. They make us ask the big questions. What else is out there? Are we connected somehow to those distant wanderers? Could life travel on a comet? What would it be like to stand on one? Those questions have driven not only science fiction stories, but real scientific inquiry. From a philosophical viewpoint, one might say comets embody the concept of the cosmic journey. They spend most of their time in darkness, far from the sun, a long cold voyage, and then for a brief time they come into the light, flourish with a tail and coma, then plunge back into darkness. It's a cycle of exile and return, not unlike the mythic hero's journey in storytelling. The comet ventures from the unknown into the known, our visible sky, and back. In that, some see a metaphor for enlightenment. We too wander in darkness seeking the light of understanding, briefly gain it, and perhaps pass it on. There's also something communal about a great comet. When Neowise, or Hale Bopp, or Halley appears, countless eyes around the world gaze at the same object. In a time where so much can divide humanity, a comet in the sky is a unifying sight. We all share one sky. Historically, unfortunately, that unity was often one of shared fear, but nowadays it can be one of shared wonder. That is no small thing. Awe is a powerful emotion that can bring people together, make them feel part of a larger whole. Comets continue to provide that experience. One can only imagine around a future campfire on Mars or a space station, colonists will point out a comet in the sky and feel that same ancestral awe and connection to each other. Finally, consider the perspective of a hypothetical cosmic narrator, a being or viewpoint as old as the stars, watching across time. Such a narrator might say, "Comets have been with you since before you knew how to speak. I have seen you fear them and adore them. I have seen you learn from them and even reach out to touch them. And through all this, the comets persist on their long orbits, indifferent but inspiring. Their gift to you is wonder, and what you have given in return is meaning." In other words, comets have no consciousness, but through us, they achieve a kind of narrative immortality. We have folded them into our story, scientific and cultural, thereby giving them a form of voice. In return, they have extended our senses and enriched our minds. Now the night deepens, and our comet, having shared so much, begins to slip away. It's time to step back into the shoes of that watcher under the night sky, you, me, any one of us, and experience a final quiet moment with the comet before it departs, taking with it everything we have learned and everything we feel, rolled into one luminous presence. The night is quiet again. Under the canopy of stars, a lone watcher stands, eyes turned heavenward. The comet that once blazed across the sky is now lower and fainter, its tail thinning into the darkness like the last wisps of a dream. The air is cool and still. There is a sense of peace, of contemplation, as the watcher keeps her gaze on that fading traveler. She reflects on what she has witnessed. In the course of this one comet's appearance, she has traveled in her mind from the birth of the solar system to the possibility of its death, from the ice in her own glass of water to the ice of interstellar space, from ancient myths to cutting-edge science. The comet, a smudge of light in the sky, has been a portal to all of that. The watcher feels small under the sprawling stars, yet oddly connected to them. The comet's long tail now a mere delicate streamer, seemed to reach out and brush the vault of heaven. It is as if the comet drew a line between earth and sky, reminding her that the boundary is only in perception, not in reality. Earth and sky are part of one continuum, and she, standing here, is part of it too. She thinks of the comet's journey. It will soon slip beyond human sight, retreating into the outer solar system. Perhaps it will return centuries hence to other watchers, or perhaps this was its only pass near the sun, and it will roam the galaxy forevermore. In either case, she feels fortunate to have seen it. Generations before her lived and died under these stars without seeing such a comet. Generations after her may long for a sight as grand, but she was here, now, to witness this cosmic wonder. The thought fills her with gratitude and a gentle melancholy, like the bittersweet feeling at the end of a beautiful piece of music. The comet's tail now is barely discernible, an extension of darkness more than a beam of light. Dawn is approaching. A subtle lightening of the eastern sky tells her the sun will soon chase away the stars. The world around her, trees and hills, are beginning to emerge as silhouettes. The time of the comet is ending for this night, and indeed, for this apparition. She takes a deep breath of the cool night air, imprinting the scene in her memory. She knows that in all likelihood she will never see this particular comet again, but its image will stay with her as long as she lives. In that way, the comet has become part of her. And through all she has learned and felt, she has, in a way, become part of the comet's story too. For a story is not just the teller, but the listener, and she has listened. In the silence, she offers a thought, perhaps a silent thank you to the comet for sharing its light, its ancient secrets, its beauty. Perhaps a goodbye, safe travels, until we meet again. If not in reality, then in the pages of a science book, or the canvas of a painting, or the strings of a violin piece composed in its honor. It's a quiet, private moment of communion between a human being and a celestial wanderer. Birds are starting to chirp. Morning's heralds. The stars are dimming. The comet is now all but lost in the brightening twilight. The watcher's vigil is over. She lowers her eyes to the horizon, where a faint blush announces the sun's imminent rise. There is a sense of completion, of harmony. The comet came, and now it goes, as has happened countless times through history. But this time, humanity understood it as never before. We rode along in our thoughts and even with our machines. We learned its composition. We passed its message. We made it ours in knowledge, even as it remains free in the sky. As the first golden arc of the sun peaks above the distant land, the watcher finally turns to head home. The comet has vanished into the morning glow, but she carries its imprint in her heart. She walks quietly, while behind her the sky grows day blue and Venus and the last stars wink out. She knows that somewhere up there, beyond the blue sky, the comet still sails away, now invisible, but real. Somewhere, far beyond the reach of her eyes, it continues on its path, a messenger heading back into the dark. It occurs to her that the comet will keep telling its story even as it leaves. To any world that intersects its trail of dust, perhaps a future spacecraft around Jupiter will sample it, or Mars's atmosphere will glean a mote. Its influence echoes even when it's gone. In the coming days, life will return to normal. The comet will become a memory shared by those who saw it, a tale to tell those who missed it. Perhaps some will feel changed by it, their perspectives broadened just a little. The watcher certainly does. As she reaches her doorstep, she pauses and looks at the brightening sky one more time. There is no trace of the comet, not even a speck, but she smiles because she knows it was there. She knows so much more about what it was and is, and yet the experience of it transcended the facts. In her mind's eye, the comet still glows, a phantom image that will stay with her. And she knows that in some sense, the comet will always be with us. Years hence, the meteors from its trail will streak through Earth's atmosphere, perhaps on some August or October night, and people will marvel at those shooting stars without realizing they owe their brilliance to this departed comet. The sky remembers, even if we humans might forget. And there will be other comets. She knows she might not see another great one in her lifetime, though she hopes she will. But certainly, others will come for future generations. Comets are part of the cosmos's ongoing story, one that will continue as long as the solar system exists and humans have eyes to look upward. Each comet is different. Each generation sees new ones. But there is a continuity too, the sense of awe they inspire. The sun is now fully above the horizon, casting its first rays on dew-laden grass. The watcher opens her door and steps inside, the warm interior welcoming after the long night. As she closes the door, she whispers a final goodbye to the comet. A goodbye that is really a until next time, whenever and wherever that may be. Outside, the sun's light floods the sky, washing away the stars of night. But though the comet has vanished from sight, it lingers in mind and memory, a gentle ghost that will long inspire stories, science, and dreams. The dark sky was pierced by a comet, sudden, bright, ancient. Its light may be gone, but the wonder it evoked in the watcher, in all of us, remains, a glowing ember in the human spirit. And as long as that wonder endures, the comet story is not over. It will return again, in books, in songs, in the sparkle of a child's eyes, learning about the cosmos, and perhaps one day in the sky once more, to amaze a future world. The cosmic story continues, and we, the watchers, will always be ready to look up and greet the next celestial wanderer with curiosity and awe.